Hello student, welcome to the GATE Academy. I hope you all are safe and fine and preparing well for the GATE exam. This time is very crucial and the GATE exam is inching closer and closer, and I hope you have prepared really well. Now you must be wondering how to revise the thing effectively. To help you out, we people have come across with this smart revision series in which today I am going to revise a very good very important subject of electrical engineering students, for electrical engineering student, which is none other than but the power electronics. So today we shall be revising this particular subject all together. You know, this subject is a very important subject of electrical engineering. It has a very high weightage as far as the GATE exam is concerned, and this subject is full of formulas and important concepts. So we shall be revising all the important formulas and concept one by one. You know, the chapters that the power electronics has: semiconductor devices, phase control rectifier, choppers or DC to DC converter, and inverter. So we shall be revising all of them one by one. So let's get started with the first chapter, that is semiconductor devices. So in semiconductor devices, I have seen one very important question coming each and every paper, and which is switch realization. Okay, so I will start with the topic switch realization. So how a particular semiconductor switch is being realized, that particularly depends upon the voltage that the device will block during its off state and the current that the device will conduct during its on state. Okay, so ideal switch can be realized by polarity of voltage that it blocks during off state, and second important thing is the current that the device carry during on state. So to realize a switch, all you have to see is the voltage that the device is going to block during its off state and the current that the device is going to conduct during its on state. Okay. Now there are basically two types of switches. One is known as the active switch and the passive switch. So if we talk about the passive switch, so in passive switch there is no control terminal. We have terminal A and B, and if suppose the voltage across the switch is Vt and the current that it carries is It, so the state of switch depends upon the voltage and the current. Good afternoon, Deepak. So the state of passive switch depends upon the voltage and current applied across the terminal A and B. So there is no control terminal in passive switches. Okay. Now if we talk about active switches, if I talk about the active switch, so in active switch we have a control terminal available called as C. So whether the device is going to on or it is going to off, that depends upon the control signal applied across this terminal C. Okay, there is no control terminal in passive switch, but there is a control terminal in active switch. So device will be on or off depending upon the control signal applied across the C. Okay. So if suppose on applying a control signal across switch across terminal C, the device turns on. So at that time, whatever direction the device is carrying current, that will and whatever voltage that it will be blocking, that will decide the quadrant of operation of a active switch. Okay. So now let us discuss all the switches one by one and see how the switches are being realized. So if I talk about the diode, the very first one, which is diode. So if I talk about diode, so diode is an uncontrolled switch. We know that Diode is an uncontrolled switch and it is a kind of passive switch. There is no control terminal. There is no control terminal in diode. Now if we see diode, so see, this is the diode that we have, terminal A and terminal B. The voltage is V and the current is I. Now you can see diode will be on. So when the diode will be on, the voltage will be 0 and current will be greater than 0. Now when diode will be off, what will happen? The voltage has to be less than 0 and the current I will be equals to 0. So these are the conditions during which the diode will get turned on and off. So if I draw the VI characteristic, or if I just realize the switch in the quadrants, so how this particular switch will be realized? Suppose this is the voltage V and this is current I. So when the diode is in on condition, it is carrying a current, and when the diode is off, it is blocking a voltage V. So the diode will be realized in quadrant number 2. When it is on, it is carrying a current in forward direction with 0 voltage drop. When it is off, it is blocking a voltage in the negative direction with 0 current. So this is how we will realize diode. So the SOA, that is safe operating area of diode, will be quadrant number 2. Okay. So this is how we will realize a diode. Now if suppose I just reverse this diode characteristic, if suppose I reverse this diode, I am having a diode in this particular direction. Now if I just reverse it, मैं इसको बिल्कुल उल्टा कर देता हूँ. अभी हम लोगों ने क्या देखा कि इसका जो कैरेक्टरिस्टिक है वो कैसा है? This is current and this is voltage. So it is operating area is quadrant number 2. If I just reverse this particular diode, इसको मैं उल्टा कर देता हूँ क्योंकि आपको ऐसी चीजें देखने को मिलेंगी. अब क्या होगा? Now this will carry current in this particular direction, so the quadrant of operation will reverse. It will carry a current in reverse direction and it will block positive voltage. So this will be the quadrant of operation for a diode in the reverse direction. So all this will be very important. You will see we will be doing some problems and which this is going to be really helpful for us. One more important formula that we have with the diode has a reverse recovery characteristic and reverse recovery time of diode. Reverse recovery time of diode, that is TRR. We calculate this by using this particular formula, 2QR upon DI upon dt. So this is a very important formula as far as diode is concerned. Its reverse recovery time, we will use this particular formula to calculate its reverse recovery time. Now after diode, let us discuss BJT. The second switch is BJT, bipolar junction transistor. So what about bipolar junction transistor? So this is the symbol of BJT. This terminal is base, this terminal is emitter and this terminal is collector. So BJT, if I ask you what about BJT, what will be the quadrant of operation of, hi Sivesh, what will be the quadrant of operation of BJT? So let us see what will be the quadrant of operation for BJT. See, if this is the voltage across the BJT and this is the current, now tell me, this is the control terminal base. Now if control signal is applied across base and the transistor is turned on, so when the transistor will be on, it will be carrying a forward current, isn't it? When the transistor will be on, it will be carrying, hi Shwakar, so it will be carrying a positive current. But when the control signal turns the transistor off, it will be blocking positive voltage, isn't it? When the control terminal turns the transistor on, it will be carrying a positive current I, isn't it? So this will be in on condition. And when the control terminal, that is base, turns the transistor off, it will be blocking a positive voltage, isn't it? Yes, Shivam, very good. So the quadrant of operation will be what? The quadrant of operation will be the first quadrant, isn't it? Now if I talk about few important points regarding BJT, so BJT is what? BJT is a fully controlled device. It is a fully controlled device. Safe operating area of BJT is what? The first quadrant. Okay, so from here you can see that the BJT will carry current in only one direction and it will block the voltage in only one direction. So it is a unipolar and unidirectional device. It is a unipolar and unidirectional device. So BJT is basically a unipolar and unidirectional device. On what basis we are deciding unipolar and unidirectional? It is blocking only one voltage, one type of voltage, so it is only unipolar, and it is carrying current in only one direction, so it is a unidirectional device. Okay, so it is a fully controlled device, unipolar and unidirectional device, and its safe operating area is what? Its safe operating area is first quadrant. Absolutely correct, Shivam. Very good. Now after BJT, let's talk about another switch, which is IGBT, insulated gate bipolar transistor. So if I talk about IGBT, what is the circuit symbol of IGBT? So this is the circuit symbol of IGBT. This is control, this is gate terminal, this is emitter terminal, and this is collector terminal. Quite similar to BJT with a little difference. BJT is a current control device while IGBT is a voltage control device. So what will be the safe operating area of this particular switch? This is quite similar to the one that we have in case of BJT. It's quite similar to BJT. When you apply a signal at gate, when the gate will turn it on, it will block, it will allow the passage of current I in positive direction. And when the gate terminal will turn the device off, it will block a positive voltage. So the operating area of BJT will be IGBT will be what? Can you tell me what will be the safe operating area of IGBT? Is it correct? Only quadrant number 1. This is on state and this is off state. So the IGBT has a switch realization in the same quadrant as we have in case of BJT. Now few points about IGBT. It is also a fully controlled device. This is also a fully controlled device. It is also a unipolar and unidirectional device because we have current and voltage only in one direction. So unipolar and unidirectional device. These are the points that you have to remember. Okay. After IGBT, let us discuss another switch. So one point that have to remember is IGBT and BJT, both of them are having the safe operating area SOA in first quadrant. Okay. While analyzing the composite switch, this will play a very important role. So you must know individual characteristics of the switches. So let's talk about the next switch and a very important switch, MOSFET, metal oxide semiconductor field effect transistor. So the circuit symbol of MOSFET is, so we have MOSFET with us. It also has 3 terminals. This is source and this is drain. Okay, and a MOSFET has inbuilt body diode. Okay, don't forget this. It has an inbuilt body diode. Okay, it has an inbuilt body diode. So if we realize this particular switch, its safe operating area will be what? Its safe operating area will be somewhat similar to IGBT and BJT, but the difference is due to the presence of this body diode, it can carry current in both direction, positive as well as negative. Okay, so if we talk about MOSFET, MOSFET is also a fully controlled device. MOSFET is also a fully controlled device. It is a unipolar but bidirectional device. Bidirectional because it can carry current in both forward and reverse direction, and that is just because of the presence of this body diode. Whether given or not given, you have to consider this body diode in case of MOSFET. So don't forget to consider this body diode. Now, so one more important point I would like to draw your attention towards, which, and it has been asked so many times, MOSFET is a majority carrier device. Okay, it is a majority carrier device. So this is all about MOSFET. Next switch that we have with us is SCR, silicon controlled rectifier, and the circuit symbol of SCR is what? Somewhat like this. We have a control terminal gate, anode and cathode. Okay, so if I draw the characteristic of SCR, if you apply forward voltage, SCR is going to block the forward voltage. If you apply the reverse voltage, it is going to block the reverse voltage as well. Okay, so it will be off in this direction and in this direction as well. It will not get turned on until and unless some signal is applied on gate with anode positive and cathode negative. So when the anode gate signal is given, the device will be turned on. So this will be the characteristic, or this will be the switch realization of SCR, isn't it? So important points about SCR. SCR is what? SCR is a semi-controlled device. This has been asked in gate exam. Okay, SCR is a semi-controlled device. Why it is a semi-controlled device? It can be turned on by application of gate signal, but it cannot be turned off with the application of gate signal. That is why it is a semi-controlled device. Looking into the VI characteristic or switch realization of safe operating area, quadrant 1 and 2 are the safe operating area for SCR. You can see it is a unidirectional. It can carry current in one direction only. So it is a unidirectional device, but it is carrying voltage of both polarity. So it will be a bipolar device. Okay. We are deciding unipolar and bipolar depending upon the voltage polarity that the device can block. Okay. And we are deciding the unidirectional, bidirectional depending upon the current direction, current that the device can carry, isn't it? So this is all about SCR. So we have these operating areas in case of SCR. After SCR we have GTO, gate turn off thyristor. Okay, so in case of GTO, what will be the circuit symbol of GTO? Quite similar to the we have in SCR, but the difference is it can be turned on and turned off with the application of gate pulse. Okay, which was not the case in case of SCR. In case of SCR, we can only turn off the device, turned on the device. Okay, by the application of gate pulse. We cannot turn off the device by the application of gate pulse, which is the case here. We can turn on as well as we can turn off the device by the application of gate pulse. So if I talk about the VI characteristic of GTO, so VI characteristics or the switch realization of GTO is quite similar to the BJT. It can block positive voltage, it can block negative voltage, and in both direction it will be off. And once you apply the gate current, it will carry positive current. Okay, so this is the VI characteristic of the GTO. And what are the important points regarding GTO? GTO is what? It is a fully controlled. Why SCR is what? SCR is semi-controlled. It is a fully controlled device. It is a fully controlled device, and it is also unidirectional. It is also unidirectional but bipolar device. Okay, so this is all about GTO. So we have a similar characteristic in case of GTO that we have in case of SCR. So now we have, after GTO, let us discuss another switch which is Triac. Triac. So what is the circuit symbol of Triac? Well, Triac anode, cathode and gate. Okay, so if we draw the VI characteristic of it, what will happen? In case of triac, it can block positive voltage, it can block negative voltage, it can carry current in forward direction, it can carry current in reverse direction as well. Okay, this terminal is popularly known as MT1 and this terminal is known as MT2. Okay, so what will happen in case of triac? We can have current in both direction and it can block voltage in both direction as we have in case of SCR and GTO. Only difference is that a triac can carry current in both direction, in from anode to MT1 to MT2 and from MT2 to MT1 as well. So it will operate on all the four quadrant. Okay, it is also a fully controlled device. And it is bidirectional because it can carry current in both direction. So it is a bidirectional and bipolar device. Bipolar just because of it can block both the voltage. So this is all about the triac. Okay, so this is how we have realized all the switches. Now let us talk about composite switches. What will happen if two switches are combined? And this is very important because this is a very pet topic of GATE exam. Composite switches. So if we have two or more than two switches, then in that case what will happen? Suppose if I have this particular switch, this is transistor and we have a diode in parallel with the transistor. Okay, so in this case what will be the safe operating area for this particular device? This is collector, this is emitter and this is base. Okay, so when two devices are connected in parallel, what will be the safe operating area for those devices? So we have a trick, you don't have to waste time upon this. We have a trick and just use this particular trick and you will get the answer. For parallel connection, what is the trick? For parallel connection, if two switches are connected in parallel, the voltage will be, when two switches are connected in parallel, the voltage will be the intersection of voltage that we get for first switch and the voltage that we get for second switch. Okay, and the current will be the union of the current that we have in case of first switch and the current that we have in case of second switch. So this is what? Intersection and union. Okay, so voltage, see, in case of a parallel combination, you know that voltage remains the same. Okay, but the current divides. So that is why when we get a parallel combination, to get the same voltage we have to take the intersection of both the voltages, and current divides, so we have to take both the current. That is why we are taking union here. Okay, so this is a very important trick. If you remember this particular trick, without wasting even a minute, you can solve all problem. Okay, so for this, let's see. So we have BJT and diode here. So if I talk about BJT, suppose this is V and this is I and this is the characteristic of BJT. And if I talk about diode, so in case of diode, okay, so what will be the safe operating area for both the devices? We have BJT with us. Okay, so in case of high current, so in case of BJT, you know that BJT blocks forward voltage and carry forward current. Okay, in case of diode, well, in case of diode, you know that it carry forward current and it blocks negative voltage, but this diode is reverse. It is connected in reverse manner. So what will happen? It will block forward voltage and it will carry current in reverse direction. Okay, if you forget this, just remember this particular thing. See, we have discussed this particular thing. If we have diode like this, then we will be having this particular safe operating area, and if we have a diode like this, ulta diode or reverse diodes, then these quadrant will just reverse. Okay, so this is the case in our case. So now what will happen? The equivalent switch. Tell me what happens with the equivalent switch. If I talk about the equivalent switch, so this is a parallel connection. So what I have told you is that in case of a parallel combination, you will take the intersection of voltages. Okay, so in case intersection of voltages mean common voltages. So you can see here the voltage is, if you take a common of these voltages, you will get this particular thing on the common characteristic, and you will take the union of the current. So this particular BJT carry forward current and diode carry reverse current. So what will happen? This will be the safe operating area of this combined switch. Okay, so this is how you will determine the safe operating area for a combination of switch, that is composite switch. This is very important as far as the GATE exam is concerned. In this year you will definitely get a question out of this topic. Okay, now let me talk about another scenario. If suppose we have switches connected in parallel. So if suppose now we are having BJT and we are having a diode which is connected in series with this BJT. So what you will do in this particular case? If suppose a diode is connected in, if suppose we have a diode connected in series with this. So if you have a series combination, just remember one thing. If you have a series combination of switches, the composite switch will have voltage. The composite switch will have voltage which is given by the intersection of both the voltages. Isn't it the same? No. We will take union here. Okay. The voltage will be given by union of voltages and the current will be given by the intersection of the currents, and this is quite usual. Okay, because if you have two switches connected in series, so in series combination you know that the current is same, so that is why you have to take the intersection of current. But in series combination you know that different devices will have different blocking voltages, so we have to take the union of this voltage to get the composite switch dimensions or safe operating area. So in that case, just tell me, we have BJT with us. So we have BJT with us and we have diode with us. Okay, and then you have to tell that what will be the composite switch safe operating area. So in case of BJT, you know it safe operating area is in first quadrant. In case of diode, you know it is, and the diode is connected in forward direction. It is not ulta connection. Okay, so you know in case of diode we have safe operating area in quadrant 2. Now what will be the safe operating area of the composite switch? So we have to take the union of the voltages. That means if you take the union of voltages, means you have to take both voltages and current intersection of current. So this will come out to be this. So this particular device will have a safe operating area in quadrant 1 and quadrant 2. Okay, isn't it? Isn't it? So this is how you will determine how composite switches will how the safe operating area of composite switches will be determined. Is that clear, student? Just give me a reply. Is there any problem? Is there any problem? Just give me a reply. Now I have two problems for you. Just see these results and tell me what will happen in both the cases. If suppose you have, and these problems are very important. Okay, so if suppose you have one switch one composite switch like this, where you have a diode and a transistor connected in series, and then you have a diode and transistor connected in series but in parallel with this combination like this. Now in this particular case, tell me what will be the safe operating area? What will be the safe operating area? So you just have done these cases. You just have done these cases. See, we have two cases connected in parallel here. Okay, this is the first case and this is the second case. So you know, this is the case of BJT connected with the diode in series. So you have just done this particular thing. So in case BJT is connected with the diode in series, you are getting quadrant 1 and quadrant 2 operation. So for the first switch, what will happen? For the first combination, you will have this particular characteristic, isn't it? And for the second combination, you will have a characteristic like this. The current direction will be reverse. Okay. Now you will add both of them and the common characteristic will be what? The common characteristic will have a shape like this. All the four quadrants will be the safe operating area. So this is how you will determine the safe operating area of a composite switch, isn't it? So once you are done with the series operation and the parallel operation, and you know all the basics of series operation and parallel operation, then if you are getting a multiple switch connected in this particular manner, you can easily find out how this particular switch is going to be realized, isn't it? If you get a multiple combination like this, you can easily determine what is the safe operating area of switch. Why am I focusing so much upon it? Because this time you are going to get a question of 2 marks from this particular topic. Okay. Now, after this, let me draw your kind attention towards the MOSFET. So I have discussed with you that we have a MOSFET in which this is a MOSFET. So we have here drain, source and gate. And what was the safe operating area for this? The safe operating area for this was, it can carry current in both direction, but it will block positive voltages. Okay. Now what will happen if suppose I just reverse this? I just reverse the drain and source connection. If suppose I just reverse the drain and source connection, so if I just reverse the drain and source connection, if suppose this is drain and source, so the connections are reversed. This is drain and this is source. So the drain and source connections are just reversed. So what will happen in this particular case? So what will be the characteristic in this case? So in this case, when drain and source are reversed, the MOSFET is still able to carry current in both direction, but the voltage that it will block will be now negative. Okay, will now be negative. Okay, so this is a MOSFET with reverse connection. MOSFET when drain and source reversed. Okay, so this is also an important case. That's why I have discussed this with you. So just remember, it will again carry current in both direction, but the voltage that it will block will be changed. Okay, from this particular thing. So this is the characteristic of a MOSFET, and this is the characteristic of or safe operating area of MOSFET when drain and source connections are reversed. Okay. So this is all about the safe operating area of devices. After that, let us talk about the BJT switching characteristics, from where we get questions. BJT switching characteristic BJT switching characteristic, and then we will see how to calculate the switching losses. Okay, how to calculate the energy loss and power from the switching characteristic. So if suppose we have a BJT, the switching characteristic, and the case will be similar in case of BJT, MOSFET and IGBT. Same calculation will be done there as well. So if suppose we have a characteristic like this, so this is known as the on time, this is the T on time, and this is known as the off time, T off time. This is the on state, and this is known as the off state. If suppose this is the total time that we have, and this particular value is VCC, this is what, this is the characteristic, switching characteristics of BJT. So we have VCA and IC coordinates here, and this particular value that we have, this is ICS. Okay, the current, that the current during the saturation state. So when the device will be on, it will be carrying full current. So this is ICS and this is voltage VCS. So if you have this particular characteristic, then what will be the E loss during on? E loss during on time, this will be given by VCC ICS upon 6 into T on, and E loss during off time, E loss during off time, this will be given by VCC ICS upon 6 into T off. So what will be the total losses? If we talk about E total, this will be E loss during on time plus E loss during off time. So this will be the total E loss. Okay, and how do you calculate the power? Power during T on, the power during T on will be average losses. So E loss during on divided by T. So this will be equals to, and you know that F is 1 upon T. So you will write E loss during on is VCC ICS upon 6 T on in upon T, that will become F. Similarly, P during power during T off, this will be equals to VCC ICS upon 6 T off into F. So these two formulas are very important formulas to calculate the energy loss and power loss, and the frequency of this topic is very high as far as the GATE exam is concerned. Regularly questions are coming from the switching characteristics of BJT, IGBT and MOSFET. So this process remains the same, only this voltage coordinates and current coordinates will change. In case if suppose this is an MOSFET, you will get a VDD here or VDS here, and you will get a drain current here. So only the coordinates, only the values will change, but the process of calculating E loss and power will remain the same. Okay, so this is one of the important topic from where we get regularly questions in the GATE exam. After that, let us discuss SCR. So in silicon controlled rectifier, SCRs, popularly also known as the thyristors. Okay, so if we discuss the thyristor, so what is the circuit symbol of thyristor? So we have a circuit symbol of thyristor like this. This is anode, this is cathode, and this is gate. And the structure of the device is, we have 4 layers, PN, PN. We have 3 junctions, J1, J2 and J3 with us, and it operates in 3 modes: forward conduction mode, forward blocking mode. So in forward blocking mode, what will happen? In forward blocking mode, this is anode and this is cathode, and we have a terminal gate here. So in forward blocking mode, what will happen? Anode is positive with respect to cathode, anode is positive with respect to cathode. J1 and J3, they are forward bias, J2 is reverse bias, okay, and the device status is off, okay, the device status is off. Second mode that we have with us is forward reverse blocking mode. Reverse blocking mode. So in reverse blocking mode, what we have? Anode is negative with respect to cathode. Anode is negative with respect to cathode, and what will happen? J1 and J3, they are reverse biased, but junction J2 is forward biased. J1 and J3 are reverse biased, but junction J2 is forward biased. So what will happen? The device is again remains in off state. The third mode that we have is known as forward conduction mode. Forward conduction mode. So what happened in case of forward conduction mode? So in forward conduction mode, anode is again positive with respect to cathode, and what happened? Gate signal is applied, okay. Gate pulse is applied and the device is in on state, device is turned on. So this is all about SCR. So SCR is a 3-junction 4-layer device. It operates in 3 modes: forward blocking mode, forward conduction mode, and forward reverse blocking mode. So this is the status. When the device is in forward conduction mode and you give gate pulse, at that time the device will turn on, okay. Now what is the VI characteristic of SCR? So if I talk about the VI characteristic of SCR, the VI characteristic of SCR will be something like this. So this is the forward blocking mode. So this is forward breakover voltage. Now if you increase the voltage, applied voltage, anode cathode voltage greater than VBO, device will turn on, but this is not recommended, as this will damage the junction J2, okay. But during the reverse mode, very little current, known as the reverse leakage current, flows. If you increase the applied voltage greater than VBR, then also device turns on, but this is not recommended as well, okay. This is not recommended as well. What is the best operation? How to turn on the device? We apply gate pulses. And then the device will turn on. So this is the application of gate pulses. If suppose this is gate pulse IG1, this is gate pulse IG2. So if you apply a higher amount of gate pulses, the device will get on quickly, okay. This particular current is known as the holding current, and this particular current is known as the latching current. So we have 2 currents with us: IL, that is latching current, IL is latching current, and IH is known as the holding current, okay. IL and IL, holding current and latching current. What is the relation between holding current and latching current? Can you tell me? Anybody? Which current is greater, holding current or latching current? latching current और holding current में कौन ज्यादा होता है, कौन कम होता है? कोई बता सकता है मुझे? Latching current is greater than holding current, or it is less than holding current, or what is the exact relation between them? Just give me a reply, anybody. Latching current and holding current, what is the relationship between them? Which one is greater and which one is less? So latching current is basically related to on process and holding current is related to off process, and we have latching current greater than holding current, and latching current is approximately 2.4 times the holding current. This is very, very important. Okay, just remember this fact. This is very, very important. Latching current is greater than holding current and latching current is exactly 2.4 times the holding current. ये पूछा जा चुका है, फिर से पूछा जा सकता है. ओके, लैचिंग करंट रिलेटेड है ऑन प्रोसेस से, होल्डिंग करंट रिलेटेड है ऑफ प्रोसेस से. सो लैचिंग करंट क्या होती है? If we applied the gate pulse, the device get turns on. But if we remove the gate pulse before actually the anode current had set up to a value which is known as latching current, the device again will again come into the off state. मतलब अगर हम गेट पल्स अप्लाई करके डिवाइस को ऑन कर रहे हैं और एनोड करंट सेटअप नहीं हुई है, उससे पहले हमने गेट पल्स हटा लिए, तब क्या होगा? डिवाइस अगेन ऑफ स्टेट पे आ जाएगी. सो हमें एक मिनिमम ड्यूरेशन के लिए गेट पल्स को अप्लाई करना होता है जब तक एनोड करंट होल्डिंग लैचिंग करंट से ज्यादा ना हो जाए, तब तक डिवाइस ऑन नहीं होती. उसके बाद अगर हम लोग गेट पल्स हटा भी लें, देन द गेट लूजेस कंट्रोल. उसके बाद गेट से कोई मतलब नहीं रहता. वी डोंट केयर अबाउट द गेट एट ऑल एंड द डिवाइस रिमेन्स इन द ऑन स्टेट. इज दैट क्लियर? So what is the minimum pulse width of the gate that is to be given? So the minimum gate pulse width that is to be given, minimum gate pulse width is given by formula. What is the formula minimum gate pulse width? Can you tell me? This is equals to LIL upon Vs. So this is the minimum gate pulse width. You have to give this amount of gate pulse width to the gate terminal. This is minimum pulse width applied at गेट. अगर इससे कम पल्स विथ देते हो गेट पर तो डिवाइस में नॉट गेट टर्न ऑन. और यहां से देख सकते हो कि जो गेट पल्स की मिनिमम विड्थ है दैट डिपेंड्स अपॉन द लैचिंग करंट एंड द इंडक्टर. तो इफ दीज वैल्यूज आर हायर द गेट पल्स रिक्वायर्ड विल बी हायर एज वेल. ओके, यहां से भी ये भी एक इंपॉर्टेंट फॉर्मूला है. दिस इज अ इंपॉर्टेंट फॉर्मूला फ्रॉम वेयर वी हैव seen questions in the gate exam, and again you will see what is the minimum pulse width of gate. It is given by LIL upon Vs. Is that clear? Yes. So ये तो रहा लैचिंग करंट के बारे में. अब होल्डिंग करंट क्या होती है? What is होल्डिंग करंट? होल्डिंग करंट इज रिलेटेड टू द ऑफ प्रोसेस. अगर हमें थायरिस्टर्स को ऑफ करना है तो क्या करना होगा? कम्यूटेशन सर्किट यूज करने पड़ेंगे. बाय यूजिंग द कम्यूटेशन सर्किट क्या करोगे? वी विल ट्राई टू रिड्यूस द एनोड करंट बिलो द होल्डिंग करंट, बिलो द होल्डिंग करंट बाय द कम्यूटेशन सर्किट. एंड इफ द हाई सुबोध, so if the anode current is reduced below the holding current, then we will apply a reverse voltage by the commutation circuit and then device will finally get turned off. So holding current is basically related to turn off process. Okay, so अगर हमें थायरिस्टर्स को ऑन करना है तो हमने देखा क्या करना होगा, और थायरिस्टर्स को अगर ऑफ करना है तो कम्यूटेशन सर्किट यूज करने पड़ेंगे. कम्यूटेशन सर्किट यूज करके एनोड करंट को हम लोग होल्डिंग करंट से बिलो लेकर आएंगे बाय द एप्लीकेशन ऑफ अ रिवर्स वोल्टेज अप्लाइड बाय द कम्यूटेशन सर्किट. सो हाउ द कम्यूटेशन सर्किट्स विल ऑपरेट, लेट अस डिस्कस वन बाय वन. सो इफ आई टॉक अबाउट कम्यूटेशन सर्किट्स और कम्यूटेशन टेक्निक्स, so if I talk about commutation techniques, what are the different techniques of commutation? So the very first one is class A commutation. We have with us class A commutation. अब ये क्या होता है भाई, इसमें क्या करते हैं? class A commutation. So in class A commutation what we have, see we have a thyristor to which we have to turn off. ठीक है. अच्छा, ये कम्यूटेशन सर्किट्स हमें तभी चाहिए होंगे जब नेचर ऑफ सप्लाई कैसा हो? डीसी. एसी के साथ किसी कम्यूटेशन सर्किट की जरूरत नहीं है क्योंकि एसी में पॉजिटिव निगेटिव पल्स 2 साइकिल होती हैं। जब निगेटिव साइकिल आएगी तो अपने आप ही थैरिस्टर्स को रिवर्स बायस कर देगी। सो वी डोंट नीड एनी commutation circuit if the supply is AC. We only need commutation circuit if the nature of supply is DC, like we have in case of inverters, choppers, etc. Okay, so the very first commutation circuit is class A commutation. So if suppose we have a thyristor to which we have to turn off. So in class 8 commutation circuits we basically have commutating element. These are known as the commutating element, L and C. So L and C are known as the commutating element. So अगर लोड में L और C हैं, so they can commutate, they can turn off the thyristor. Okay, they can turn off the thyristor. So this is latching current if suppose commutating element, and this is the load that we have. Okay. So what will be the value of current at the output? The output पे जो value of current होगी, that current is, let me write this here, so we will get the enough space for this. These are commutating element. So what is the value of current that we will be having? This is given by Vs upon omega RL e to the power minus del t sin omega RT. Okay, so this is the current that we have in this particular circuit. If I draw this particular current, you can see after this particular time t, what will happen? After this particular time t, this current I naught or IL, this will become 0. Okay, so if we have these commutating element in the circuit, the current is automatically getting equal to 0 after certain time t, and that time t is known as what? That time t is known as, see, when I naught will become 0, what will happen? Omega RT, this will be equals to pi. So T will be equals to pi upon omega R. So after this time, the current will decay to 0, or it will come down below holding current, and the device will get turned off. So this is how the load commutating element helped in the commutation of thyristors. Okay, so T equals to pi by omega R, where omega R is what? Omega R is known as the ringing frequency. So omega R is equals to omega naught square minus del square. Del is the damping factor, and it is equals to R upon 2L. Okay, this is also known as zeta. So for this particular circuit, it will be able to commutate this thyristor if this particular condition, that is R square must be less than 4L by C, that is circuit must be underdamped, or zeta must be less than 1 is satisfied. Okay, so if we have load commutating element in the load, we can commutate the thyristors like this. So this commutation is known as class 8 commutation. One thing that is being asked regularly, and what is the value of omega naught, we didn't discuss. It is equals to 1 upon under root LC. One thing that is being asked from this particular circuit is for how much time this thyristor will conduct, or what will be the commutation time for this thyristor. So this is given by pi upon omega R. Okay, this is all about class A commutation. Now let us discuss class B commutation, or which is popularly known as the current commutation. The current commutation. So we have a special circuit for this. So we have a main thyristor to which we have to turn off, and to help this process out, we have an auxiliary thyristor with us, and we have commutating element present in this circuit as well, and then we have a diode here. Then this is connected to load. So this is basically the load that we have. This is voltage Vs, this is Vc, and this current is Ic. So what we have to do, this is current I0, this voltage is V0. This is the main thyristor current ITM. So this is the circuit popularly known as the current commutation circuit that we use to commutate the main thyristor. Now, what are the important formulas related to this particular circuit? So the important formulas related to this particular circuits are, what will be the ITM peak? What will be the peak current that the main thyristor carry? It will be equals to I0. What will be the ITA peak? What will the peak current of that thyristor, auxiliary thyristor will contain? This is equals to IP or Vs under root C by L. These are very important formulas. Several times the questions have been asked from these formulas. So ITM peak will be equals to I0. ITA peak will be equals to IP, that is the peak value of IC. Is that clear? Just give me a reply बच्चा लोग. Is that clear? ये दो फॉर्मूले बहुत इंपॉर्टेंट हैं. These two formulas are very important as far as the gate exam is concerned regarding current commutation. After that, see, ITM current during normal condition, this will be equals to I0 minus IC. Okay. What is IC? IC is basically IP sine omega naught T. So you can see from here, if I0 is equals to IC or IC reaches to I0, what will happen? ITM will be equals to 0 and main thyristor will get off. So when the main thyristor will get off, when I0 become equals to IC. So we have I0 and IC is equals to IP sine omega naught T2. Suppose we call this duration at T2. So what will be the value of T2? This T2 will be equals to 1 upon omega naught sine inverse I0 upon IP. So this will be the duration, this will be the value of duration T2 during which the reverse voltage will be applied across this main thyristor via this capacitor to turn this main thyristor off. Okay. So this is also an important formula that we have. Is that clear? Just give me a reply. Is that clear? Now what will be the conduction time for auxiliary thyristor? The conduction time for auxiliary thyristor will be pi under root LC. What will be the conduction time for main thyristor? The conduction time for main thyristor will be this time plus T2 time added in it. So omega naught is basically equals to 1 upon under root LC. So if you put omega naught here, you will get under root LC sine inverse I0 upon IP. So this will be the time for which main thyristor will be conducting. So what will be the TM minimum? So TM minimum, this will be equals to pi under root LC, and what will be the TM max? So TM max will be equals to 3 by 2 pi under root LC. So this will be the minimum and maximum time for which the main thyristor will conduct. Okay. After that, what will be the reverse voltage applied across the thyristor? So the reverse voltage applied across the thyristor, main thyristor, this is equals to Vs cos omega naught T2, and you know what is the value of omega naught T2. I have just calculated. This is equals to sine inverse I0 upon IP. This is the reverse voltage that will be applied across thyristor. What will be the circuit turn off time? What will be the circuit turn off time TCM? This will be equals to this voltage CVR upon I0. This is the circuit turn off time. So we have these important formulas with us from where regularly gate authority have asked questions. Is that clear बच्चा लोग? Just give me a reply. Auxiliary thyristor का minimum conduction time क्या है? Pi under root LC. What is the Conduction time for main thyristor pi under root LC per under root LC sin inverse I naught upon IP. What is the minimum time for which main thyristor conduct pi under root LC? What is the maximum time for which main thyristor conduct 3 by 2 pi under root LC? Okay, and peak value of current through main thyristor is I naught, and through auxiliary thyristor this is equals to IP. So these are the important formulas related to the current commutation. After current commutation we have voltage commutation with us. So the next topic is voltage commutation. सो वोल्टेज कम्यूटेशन का सर्किट कैसा होता है, जल्दी से देखते हैं. ये होता है मेन थायरिस्टर, देन वी हैव कैपेसिटर इंस्टॉल्ड हेयर. आफ्टर दैट वी अगेन हैव द ऑक्सिलरी थायरिस्टर, दिस इज TM, दिस इज TA, and we have inductor, then we have diode. So this is the commutation circuit. Then we have freewheeling diode in this particular case as well, and then we have load connected. So this is load, this is freewheeling diode, this is current I naught, this is voltage V naught, this is the main thyristor, diode, this is L, this is the capacitor C. So we have this particular circuit with us in current commutation. Now again, that we have calculated in case of current commutation, similarly in case of voltage commutation, what will be the ITM peak value of current through main thyristor? So this will be equals to I naught plus IP, that is I naught plus VS under root C by L. होगा कि नहीं होगा बच्चा लोग, जल्दी बोलो, होगा ना. इसके बाद what will be the ITA peak? So ITA peak in this case is equals to I naught. These two are very important formulas, और ये फॉर्मूला से मैंने एक बार नहीं कई बार गेट में क्वेश्चन देखा है. सो ये फॉर्मूला बहुत ही ज्यादा इंपॉर्टेंट है. दिस फॉर्मूला इज वेरी इंपॉर्टेंट. व्हाट इज द पीक करंट ऑफ peak value of current across main thyristor? This is I naught plus Vs under root C by L. Okay, now circuit turn off time in case of this particular circuit will be equals to CVS upon I naught. Another important thing is commutation interval. So if you are asked for calculation of commutation interval, this is equals to 2 time TCM. What is the T effective? T effective here is T on plus this 2 TCM. Okay, T on plus 2 TCM. So what will be the value of V naught average? So the value of V naught average will be Vs upon T into T effective. Let me write this T on effective. This is known as T on effective on time. Okay, so this is how you will calculate the average voltage in case of current commutation, voltage commutation circuit. So all these are the important formulas related to the current commutation circuit. Okay, out of which I rate this particular formulas to be very important. Okay, you will definitely get question out of these formulas. Just have to remember these formulas and you will get score 1 or 2 marks whatever this particular question will contain. Okay, is that clear बच्चा लोग? Just give me a reply. After that we have last commutation circuit, which is known as impulse commutation. Impulse commutation or complementary commutation. Impulse commutation or complementary commutation. What is the circuit for this particular If we have Vs voltage, then the circuit for this particular commutation circuit will be like this. Resistance R, then we have T1 with us, then we have resistance R2, then we have T2 with us. So this is T1, this is T2, and we have a capacitor connected here to help in the process of commutation. This is R1, this is R2. Now, what will be the IT1 peak? So the IT1 peak will be equals to Vs upon R1 plus 2 Vs upon R2. And what will be the IT2 peak? IT2 peak will be equals to Vs upon R2 plus 2 Vs upon R1. So these are the two important formulas that we have in case of complementary or impulse commutation. After that, you are asked to calculate the circuit turn off time for TC1, which is equals to R1C ln 2, and don't write here 1 because they will be same. Circuit turn off time in case of second R2C ln 2. Now you will get two values of C. Here. So which one to choose? The higher value of C will be chosen. Higher value of C will be chosen. Okay, so these are the formulas related to complementary commutation. These are very, very important. IT1 peak you will calculate by Vs upon R1 plus 2 Vs upon R2. IT2 peak you will calculate by Vs upon R2 plus 2 Vs upon R1. Okay, so this is all about commutation circuit and chapter number 1. After the chapter number 1, we will move towards to chapter number 2, which is phase controlled rectifiers. Phase controlled rectifiers. So phase controlled rectifier, what they will do in case of phase controlled rectifier, we have fixed AC and we will convert that fixed AC into variable DC. Okay. So if I talk about single phase half wave controlled converter, if I talk about single phase half wave controlled converters, so in case of single phase half wave controlled converter, the circuit look like something like this. So we have AC source and we have thyristor connected between source and load. Here we want DC supply. This is source current and this is the load current I0. This is thyristor and this is Vs, or we may call it Vm sin omega t. This is Vs equals to Vm sin omega t. So this is the circuit of single phase half wave controlled rectifier. Now in this particular case we have different loads with us. Okay, suppose the load is R, or suppose the load is, we have different load with us. So first load is R or R load. Let me write it. R load or RL load with freewheeling diode. Second case that we have is RL load, and third case that we will have is RLE load. So load can be out of these four. It can be a R load, purely resistive load, it can be an RL load, or it can be an RL load with freewheeling diode, and it can be an RLE load. So what will be the different formulas or different values of voltages in this case? Since this is a half wave control rectifier, so for a complete input cycle we will be having only a half pulse in the output. So what will be the value of output voltage in case of this particular case. Let me mark a division line between them. So output voltage in this particular case, this is given by 1 upon 2 pi alpha to pi Vm sin omega t d omega t, and if you calculate it, you will get Vm upon 2 pi 1 plus cos alpha. So this is the formula of average output voltage in case of R load or in case of RL load with freewheeling diode. So this is how you will calculate the average output voltage. Average output current I naught average will be V naught average by R, and circuit turn off time will be equals to pi by omega. Okay. In case of, so you know the limit of integration in case all the cases. In case of RL load, this output voltage will be V naught average will be 1 upon 2 pi. The limit of integration will be alpha to beta Vm sin omega t d omega t, where beta is known as the extinction angle. Beta is known as the extinction angle. So in case of inductive load, there is a negative spike in the voltage, or the power transfer from load to source takes place for alpha to beta, that we know. Okay. So what will be the V naught average value here? So V naught average, this will be equals to Vm upon 2 pi cos alpha minus of cos beta. This is V naught average in case of RL load. I naught average will be calculated from V naught average by R as well, and circuit turn off time, this will be equals to pi minus beta upon omega. And what will happen here for alpha to pi, the power transfer from source to load, and for alpha to beta, the power transfer from load to source. So this is the problem, the power transfer from load to source, and that's why in this particular case we installed a freewheeling diode in parallel. Like in this circuit, we will have a freewheeling diode which is optional. If we have RL load, then we will connect this freewheeling diode in this circuit. So if you have RL load, so we will connect this freewheeling diode in the circuit, so that what will happen, the negative spike of the voltage will be removed and the power will be now transferred completely to the load only. Okay. In case of RLE load, so in case of RLE load, we have E present in the load. So due to the presence of E, there is a limitation on firing angle. When Vm sin omega t is equals to E, or we may say Vm sin theta 1 is equals to E, so this theta 1 will be equals to sin inverse E upon V. So the firing angle must lie in this particular range. It must be greater than theta 1 and it must be less than pi minus theta 1. This is the condition that we have. I naught is given by Vm sin omega naught t minus E upon R. So what will be the average value of I naught? So I naught average will be equals to 1 upon 2 pi R alpha to beta Vm sin omega t minus E d omega t. From this particular formula you will calculate average output current in case of RLE load. After that, when you apply the KVL, that is V naught equals to E plus I naught R, from here you can calculate the average output voltage in case of an RLE load. Okay, so this is how you will do the calculation. These formulas will be used in case of RLE load. You have to remember these formulas in this particular conditions, and whatever question will be there, by using these particular formula you will be solve them easily. Okay. Now we haven't calculated the RMS value in any of the case, because We have a formula of calculation of RMS value, and this particular formula is RMS is 1 upon under root 2 into time period, high limit minus low limit plus half sine 2 omega t, and low limit minus high limit whole to the power 1 by 2. Okay. So this is the formula of calculation of RMS value in general. By using this particular formula, or by remembering this particular formula, if you just remember this particular formula, then you can see here, you know the limit of integration in all three cases. The limit of integration in this particular case is alpha to pi, alpha to beta, and it is alpha to beta here as well. So you know the limit of integration. So just by putting the values in the RMS value formula that I have just discussed with you, you can calculate the RMS value in any of the cases by using this particular formula. Okay. So this is all about the half wave controlled rectifiers. After that we have full controlled rectifier. Fully controlled rectifier. So under full control rectifier we have single phase cases and three phase cases. Under single phase cases we have single phase full wave control rectifier and single phase semi control rectifier. So let us discuss the formulas of each one of them one by one. So if I talk about single phase full controlled rectifier, so in case of single phase full wave control rectifier, what is the circuit diagram of it? So we have 4 thyristors connected in this particular manner, and we have a AC source connected between them. This is the load that we have, and let's suppose this load is highly inductive load. This is what we have. This current is I naught, this voltage is V naught. This is thyristor T1, this is T2, this is T3, and this thyristor is T4. So what are the values of what are the waveforms of output voltage, input current, output voltage and input current, the two important waveform that we have. So we will be having, in case of voltage, we will be having a waveform like this. So during this interval T1, T2 conduct, and during this interval T3, T4 conduct. This is alpha, this is pi, and this is pi plus alpha, this is 2 pi, and this is 2 pi plus alpha. So this is V naught, and if I draw the IS current, then IS current will be what? Source current. Source current will be what? The value of source current will be something like this. Okay, this magnitude is what? This magnitude is I naught, and this magnitude is minus of I naught. So these are the output voltage and source current that we obtain in case of single phase full wave control rectifier in case of highly inductive load. Now what will be the average output voltage? So if we calculate the average output voltage, so the average output voltage, this will be equals to 1 upon pi. You can see here the time period is pi, and we will integrate the voltage waveform from alpha to pi plus alpha. So what will happen? V naught average will be equals to alpha to pi plus alpha. We will integrate Vm sine omega t d omega t, and after that what you will get? You will get 2 Vm by pi cos alpha. So this is how you will calculate the average output voltage, and this is very important. Second thing, if you calculate the RMS value, then you will get Vm by root 2 or Vs. The RMS value in case of single phase full wave rectifier is Vm by root 2 or Vs is what we have. Is that clear? After that, tell me what will be the value of source current ISR RMS. This will be equals to what? You can see this particular waveform. So ISR source current RMS value will be equals to what? This is equals to I naught, isn't it? The RMS value of source current will be equals to I naught. This is very important. Okay. Now if we write the Fourier series expansion, of the source current, then what you will get? The Fourier series expansion of source current will be n equals to 135 to infinite. This is equals to 4 I naught upon n pi sin n omega t minus n alpha. So this is the Fourier series expansion of this source current waveform. Okay. Now after that we will define a term which is known as the current distortion factor. Current distortion factor, or also known as CDF. So what is the value of current distortion factor CDF? This is equals to RMS value of fundamental component upon RMS value of total component. Current distortion factor CDF is RMS value of fundamental component upon RMS value of total component. So you will get fundamental component from this particular Fourier series waveform. If you put n equals to 1 and divide it by root 2, you will get fundamental component. So what will be the fundamental component? IS1 RMS. This will be equals to 4 I naught upon root 2 pi, or we may also say 2 root 2 I naught upon pi. So this will be the fundamental component. How do you calculate it? You just put this fundamental component will be 4 I naught upon n pi. You just calculate the RMS value of this particular component by putting n equals to 1 here. And then after CDF will be what? CDF is equals to IS1 RMS upon IS RMS, that is total current. So what will be the value of it? It is equals to 2 root 2 upon pi I naught upon I naught. This is equals to 2 root 2 upon pi. This is very important. After that we define fundamental displacement factor, which is equals to cos of alpha. Okay. We have phi n here, which is equals to minus of n alpha. So fundamental displacement factor is basically equals to what? It is basically equals to cos of phi 1 and we have cos of alpha. After that we have power factor. So what will be the power factors? The power factor is equals to CDF into displacement factor. CDF into displacement factor. So this will be equals to 2 root 2 upon pi cos alpha. So if you know what is the firing angle, you can easily calculate the power factor, my dear student. This is the value of, this is the formula of calculation of power factor, 2 root 2 upon pi cos alpha. Okay. After that we will calculate total harmonic distortion. Total harmonic distortion or THD. So the THD is equals to under root 1 upon CDF square minus 1. So when you put this particular value of CDF here, which is equals to under root 1 upon 2 root 2 upon pi square minus 1, you will get a THD of 48.3% here. So this is how you will calculate all these values. So the important formula to remember is, and then you can derive all other things. The value of RMS source current is I naught. Average output voltage is equals to 2 Vm by pi cos alpha. And the Fourier series, if you remember the Fourier series of this particular waveform, you can do all the calculation, whether it is CDF, whether it is DF, whether it is THD. Is that clear? Just give me a reply, bachcha log. Is that clear? Very good. Now, after single phase full wave converter, we have single phase semi converter. Single phase semi converter. So, see, single phase semi converter. What is the circuit diagram? So, we have this particular circuit diagram with us. So, this circuit is known as, this is T1, this is D1, this is T2, this is D2, and this is the freewheeling diode, this is I naught, this is plus minus V naught that we have. So, single phase semi converter is some different from single phase full converter. Here we have diodes connected across the branches of thyristor, and we have a freewheeling diode as well. And single phase semi converter is better than this single phase full converter, okay, due to this freewheeling diode. We know that when in case of single phase full converter, we are getting a negative spike in the voltage. So during that duration, pi to pi plus alpha, what will happen? The power will flow from load to source, which is not desired. Okay, by using this semi converter in which we have freewheeling diode as well, that negative spike will disappear. So now what will happen? During the movement pi to pi plus alpha, when the power was flowing from source to load to source, that power will again be through freewheeling diode, will again be flowing through the dissipated through the resistor. So the power consumption will be improved in case of semi converter. That's why semi converters are better than the full converters. Okay. Now, so what is the waveform if I talk about? So if voltage waveform I talk about, there will be no negative spike. You can see here there will be no negative spike in the voltage during alpha to pi, and this is for pi plus alpha to 2 pi. So during this movement T1 D2 will conduct, and during this movement T2 D1 will conduct, and this is the moment where freewheeling diode will be conducting. So this is the output voltage waveform. And if I talk about the source voltage waveform, so the source voltage waveform will now have a quasi nature. During alpha to pi, it will be plus I naught, and during pi plus alpha to 2 pi, it will be having a magnitude equals to minus of I naught. So this will be the source waveform. So now if I talk about, if we calculate V naught average, then what will be the value of V naught average? This will be equals to 1 upon pi alpha to pi Vm sin omega t d omega t, and this is equals to Vm by pi 1 plus cos alpha. So this is the average value of output voltage that we will calculate. So this is V naught average that we have, and after that what will be the value of source current? This is source current, let me correct it. This is source current. So what will be the RMS value of source current? So the source current RMS value, this will be equals to I naught under root pi minus alpha upon pi. So this will be the value of RMS source current. So the output voltage in case of semi converter will be Vm by pi 1 plus cos alpha. RMS value of source current will be I naught under root pi minus alpha upon alpha. See, in case of phase control rectifiers, if you know the formula, then you don't have to know anything. Okay, there are direct questions asked from phase control rectifiers in which you know, if you know the formula, you are definitely going to solve the question and the marks will be yours. Okay, but if you don't remember the formula, then what will happen if you are trying to derive those formula? If you have better practice, then that's fine. But if you don't remember the formula in case of phase control rectifier, then you are going to waste your time in solving the question. So it is a better practice to remember formulas in case of phase controlled rectifier. Okay. Now if I write the Fourier series as we have written in case of single phase full converter, then in case of single phase semi converter, what will be the Fourier series of source current? This will be equals to n equals to 135 to infinite 4 I naught upon n pi that we have, and apart from that we have cos n alpha by 2 sin n omega t minus n alpha, sin n omega t minus n alpha. This is what we have in case of, we have n alpha by 2 here as well. So this is the formula of, this is the Fourier series in case of semi converter. Now like we did in case of full converter, you can calculate the CDF. You can calculate the CDF. CDF is what? CDF is RMS value of fundamental component upon RMS value of total component. Then you can calculate the fundamental displacement factor, which is equals to cos of alpha by 2. Then you can calculate power factor, which is equals to CDF into FDF. And after that you can calculate the THD, which is equals to under root 1 upon CDF square minus 1. So by knowing this particular Fourier series, you can calculate all the related things. Okay. So you can see there is quite similarity in both the cases. Here we have 4 I naught upon n pi, where here we have 4 I naught upon n pi sin n omega t minus n alpha. You have to add a cos n alpha by 2 here and have to do n alpha by 2 here to convert this Fourier series into semi converter. So this is quite easy to remember and you can remember it quite easily. So this is all about single phase full wave converters. We have discussed single phase full converter and semi converters. This is all about full wave converters. Now let us discuss the three phase converter. So like we have in full converter, we have here also three phase full converter and three phase semi converter. So three phase full converter, if you talk about three phase full converter, there will be one extra branch added in it. So let me just write the formula that we use in case of three phase full converter. So average V naught here, this is equals to 1 upon pi by 3. Limit of integration will be pi by 3 to 2 pi by 3 plus alpha VML. This is the maximum value of line voltage sin omega t d omega t, and after solving it you will get 3 VML upon pi cos alpha. So this is the average output voltage in case of a three phase full wave converter. Another important thing is the value of source current, RMS value of source current, that is ISR, and this is equals to I naught under root 2 by 3. Most important formula that you must have to remember, because several times the questions have been asked in which they demanded you to calculate the RMS value of the source current, and it is equals to I naught under root 2 by 3. I naught is the output current which will be given to you. Is that clear? Is that clear? Just give me a reply. Is that clear? And after that, one thing that you have to remember is the Fourier series expansion in case of three phase converter. So the Fourier series expansion in case of three phase converter, this is equals to summation n equals to 6k plus minus 1. So if you put values of k, you will get 5, 7, 11, 13. So in case of three-phase converter, even harmonics and triple N harmonics are absent. Very important thing. Questions are asked from this particular thing as well. So I will make you note this particular thing. First, just let me write this expression. So this will be 4 I naught upon n pi. We have an extra sign n pi by 3 added, sin n omega t plus n alpha. Okay. So the expression is still quite similar that we have in case of single phase full converter. We have 4 I naught upon n pi sin n omega t minus n alpha. In case of single phase semi converter, you have to add cos n alpha by 2. In case of three phase full converter, you have to add sin n pi by 3 here. So this is how you will remember this particular formula. Okay. One important thing is that even and triple N harmonics will cancel due to symmetry. Even and triple N harmonics are absent. Even and triple N harmonics are absent. This is very important. Okay, there are questions I have seen. They will write that in three phase full converter, the fundamental frequency is 50 Hz. What will be the next frequency of next harmonic? So you can see the next harmonic component will be what? If fundamental is having a frequency of 50, then next harmonic will be having a frequency of what? See, it starts from fifth. So the next harmonic will have a frequency of 5 into 50, that is 250. Okay, not 150, because third harmonic is absent in case of three phase full converter. So this is what you have to remember. And after this particular session, you can see there are previous year question in which this particular thing has been asked several times. Okay, so this is going to help you out in a great manner, my dear student. Now after that, if you calculate CDF, which is equals to IS1 fundamental RMS upon IS total RMS, you will get a value 3 upon pi. Okay, FDF here is cos of alpha. So the power factor will be equals to what? It will be equals to 3 by pi cos alpha. So if you know this particular formula, you can directly calculate the power factor just by knowing the value of firing angle. Okay. Now if you calculate THD in this particular case, so THD will be equals to 1 upon CDF square minus 1, which will be equals to 31%. Okay, this is having a fixed value. It will be equals to 31% here. Is that clear? So all these are the necessary and important formula of three phase full converter, my dear students. After that, if I talk about three phase semi converter, if I talk about three phase semi converter, so in three phase semi converter, what is the value of output voltage? We will be having an average value of output voltage given by 3 VML upon 2 pi, 3 VML upon 2 pi 1 plus cos alpha. This will be the average output voltage. And in case of RMS value of source current, we are having two formulas, which is equals to I naught pi minus alpha upon pi to the power 1 by 2, similar to single phase semi converter case when the value of alpha, okay, when the value of alpha is greater than 60. But it is equals to the same formula that we have obtained in full converter, I naught under root 2 by 3 when alpha is less than 60. That is what you have to remember. Is that clear? This is something that you have to remember. Okay. So this is all about single phase. So this is all about full phase control rectifier. One last thing I would like to tell you, if suppose you are asked, see, don't forget to remember these formulas. Always apply this particular formula, V naught equals to E plus I naught R when the load is RLE type, okay, and V naught equals to I naught R when the load is R or RL type, okay. you will ignore the inductor because average voltage across inductor is what? It is equals to 0. Okay. Now, one thing that you will do, equate P input to P output, and P input will be equals to VSR ISR into power factor, and P output will be equals to V naught I naught in case of R load. And let me discuss in general. Is suppose you have RLE load, then in case of RLE load you will be able to calculate this by I naught RMS square into R plus E naught I naught average. Okay, in case of complete RLE load. Now, if suppose you have only RL load, you will only use I naught square R. If you have RLE load, you will use this particular thing. Okay, so L will be ignored in this particular case as well, because average power absorbed across inductor is also 0. Okay, so you will use this particular formula for calculation of power factor, and this particular KVL for calculation of any of the thing. Okay. Now, let me tell you one more thing. For example, if I talk about single phase full wave converter, so V naught is equals to 2 Vm by pi cos alpha. Okay, in this particular case you will apply V naught equals to E plus I naught R when your alpha is less than 30. Okay, the converter will behave like an rectifier, but what will happen? You will use this particular formula V naught equals to E minus E plus I naught R when alpha becomes greater than 90, because the rectifier is now converted into line commutated inverter. Okay, if alpha is greater than 90, you have to use this particular formula. V naught is minus E plus I naught R, because rectifier is now converted into line commutated inverter, because when you put cos alpha to be greater than 90, you will get a negative voltage. Okay, that means inverse operation. So the rectifier is now working as an inverter. So the polarity of E has to be reverse. Okay, so the polarity of E has to be reverse. So always remember this particular point. Okay, this is very, very important. So this note is very important. This note is very, very important, and this note is also very, very important. If you remember these particular things, you will never commit a mistake, and you will get full marks out of this particular topic in your GATE exam. Is that clear, students? Just give me a reply. I am waiting for your reply. Is that clear? Just give me a reply. Fatafat. Are you getting all the things? Now, one more important topic, very, very important topic, or very, very liked topic by a topic that is very much liked by the GATE authority. Okay, and that topic is what? Effect of source inductance. Okay. And students, I have seen that you people are very, very confused regarding that. You आप लोग अपने आप को बहुत उलझा लेते हो सोर्स इंडक्टेंस के फॉर्मूला में. सो मैं आपको बताने जा रहा हूं आपको कौन कौन से फॉर्मूले याद करने हैं. आई एम जस्ट गोइंग टू टेल यू which particular formula you have to remember. Okay. Thank you Shiva, thank you Swakar. I hope this revision is helping you out. Okay. So effect of source inductance, इतने कम समय में पावर इलेक्ट्रॉनिक्स बहुत जल्दी हम लोग रिवाइज करने वाले हैं यार. तो कॉपी पेन लेके बैठे हो गए, मुझे पता है. नोट करते जाओ और फटाफट नोट करते जाओ, ये ट्रिक्स नोट करते जाओ. लास्ट टाइम पे ये ट्रिक्स अगर याद रखोगे ना, इफ यू रिमेंबर दीज ट्रिक्स एट द लास्ट टाइम ना, you will never commit a mistake. Only thing that you have to do is to avoid silly mistakes that will certainly lower down your rank. Okay, I know you are well prepared, so only thing that you have to remember here, just note them down. So effect of source inductance, if we talk about, let us discuss three cases. First case, single pulse. So if you have single pulse converter, then in that case What is the output voltage of single pulse converter? Vm by pi, Vm by 2 pi, 1 plus cos alpha. Now due to source inductance, the average voltage gets a reduction, and that reduction factor in case of this particular case single pulse converter will be FLS I naught, where I naught average, this will be equals to Vm upon omega Ls cos alpha minus cos alpha plus mu. Mu is what? Mu is overlap angle, overlapping angle. Okay. So due to the source inductance, the net average voltage experiences a reduction, and that reduction is what? In single phase we have FLS I naught. In case of two pulse converter, that is full wave converter, output voltage is what? It is equals to 2 Vm by pi cos alpha if there is no source inductance. But if source inductance is there, what will happen? You will subtract a term 4 FLS I naught. Okay, just remember this fact. This factor you have to subtract from a normal case to get the average output voltage in case source inductance is present. And this output current is given by Vm by 2 omega Ls cos alpha minus cos alpha plus mu. Just remember these formulas. There will certainly be a question from here. There will certainly be a question from here. Out of this complete phase control rectifier, if I talk about this topic, has 50% probability of giving questions into the exam. Okay. Now, if I talk about a 6 pulse converter. So, in a 6 pulse converter, you know what is the value of output voltage? It is equals to 3 VML upon pi cos alpha. If there is no source inductance, but if there is source inductance, what you will do? You will just subtract 6 FLS I naught from it, and you will get the output voltage. Output current will remain same as you have in case of 2 pulse converter, but now Vm will be converted into VL. So we will be having VL upon 2 omega Ls cos alpha minus cos alpha plus mu. इतने से फॉर्मूले हैं यार. Only these particular formulas is what you have to remember, and this particular topic will be done. Okay. Now, inductive voltage regulation. In this case, voltage regulation is something that may be asked. So it is equals to cos alpha minus cos alpha plus mu by 2. Cos alpha minus cos alpha plus mu by 2. Okay, this is what? Inductive voltage regulation. And what will be the value of CDF? FDF, sorry. FDF has a value here equals to cos alpha plus mu by 2. यार तो इतना तो याद रख ही सकते हो ना. You can remember this silly thing. So this is all about the phase controlled rectifiers. So phase controlled rectifiers are done now. Okay. So phase control rectifiers are done now. So far now we have discussed the semiconductor devices and the phase control rectifiers. Now after that we will start with the chopper circuit, DC to DC converters or chopper circuit. And for that, let me take a break of 5 minutes, and you also take a break of 5 minutes, and then we will join again. Okay. So hello student, welcome back. So we are done with semiconductor devices, we are done with phase control rectifier. Now it's time for the choppers, a topic from where alone you will get 3 to 4 marks. Okay, a topic that is very important. Okay, you will get around 3 to 4 marks out of these topics only. So what are choppers? Choppers are basically DC to DC converter. If you have a fixed voltage DC and you want to convert into variable DC, you will use DC to DC converter or choppers. Okay. So in choppers we have basically three circuits. Buck converter, that will step down the available DC. Boost converter, that will step up the DC, and buck boost converter, which will do the both for you. Okay. So let us discuss one by one. So first start with the buck converter. So the first circuit is buck converter. So what is the circuit diagram for it? So in buck converter we have available DC voltage, we have a switch, we have a freewheeling diode, and after that we have an inductor, capacitor acting as a filter, and then finally we have a load. So this is the load that we have. This is I naught current, this is capacitor, the current across it is IC, this is the voltage, and across inductor this is the reference polarity of voltage and current, this is the freewheeling diode, this is the switch, or this is popularly known as the chopper, this is Vs voltage, this current is the source current. So this is all about the circuit that we have in buck converter. So this circuit will do what? This circuit will give you output voltage which is less than the input voltage. Okay. So now what will happen? Now what will happen if I draw the inductor voltage waveform? If I draw the inductor voltage waveform, what will be the voltage across inductor when the switch is on? Before actually getting into the buck boost converter, let me define the duty ratio first. So I hope you all know about duty ratio. If I denote it by alpha, this is equals to T on upon T, or T on is the on time, T is the total time. So basically T on must be written as alpha T, and we have T off time which is equals to 1 minus alpha T. After that we have switching frequency which is equals to 1 upon T. So if I talk about the inductor voltage, then when the switch is on, what will be the inductor voltage? When the switch is on, the inductor voltage is, let me draw following waveform. If I draw IL, VL, IL, and then I will draw the I switch current waveform or chopper waveform, switch waveform, and then I will draw this I FD waveform. Okay, these all are the things that we have to calculate. So let me draw these waveform and we will discuss them one by one, what will happen with them. So this is the time axis that we have. Now tell me what will happen with the inductor voltage when the switch is on. This particular time is what? This time is the on time. This is the on time that we have, and this particular time is the off time that we have. So during the on time, the inductor voltage will be what? Vs minus V naught. So during the on time, the inductor voltage is Vs minus V naught. So this magnitude is Vs minus V naught. During the off time, when the chopper will be off and the freewheeling diode will be conducting, okay, during the on time, which part of circuit will be active? So this part of circuit will be active during the on time, okay, and during the off time, only this particular part of circuit will be active during off time. This is during on time. So during on time, what will the VL voltage? The VL voltage will be minus of V naught, okay. This VL voltage will be minus of V naught, and then this cycle repeats. So this is what? This is minus of V naught during off time. What about the inductor current? What about the inductor current? The inductor current will increase from minimum value to maximum value during on time, and then it will decrease from maximum to minimum value during this particular time, and the average of inductor current IL average in this particular case, this is equals to I naught, which is equals to V naught by R. So this is the maximum value of inductor current, and this is the minimum value of inductor current that we have. Okay, and one more thing, this is the ripple current, which is known as del of IL. So this is the pattern of inductor current, how inductor current varies. Now see, the switch will carry the part of inductor current during when it was on. So what will be the switch current? The switch current will be something like this, isn't it? The switch current will be something like this. Now diode will carry the part of inductor current when switch is off and the diode is on. So what will be the diode current? The part of inductor current that we have during the off period will be the diode current, isn't it? So if suppose this is the average value of switch current, this is the average value of diode current. So if I talk about what will be the average switch current, so this average switch current will be what? This is equals to alpha times, this will be equals to alpha times the IL average, and if I talk about the freewheeling diode average current, this will be equals to 1 minus alpha times IL average, isn't it? Because switch current is only present during the on period, so you may write as a proportion of IL average, switch current may be written as alpha times IL average, and freewheeling diode is present, current is present during the off time, so you may write it, the average value of it equals to 1 minus alpha IL average. Okay, so if you just remember these particular thing, see how easy this will become. Okay, so if I talk about what will be the VL average, so tell me what will be the value of VL average. VL average, this will be equals to 0 because the inductor current is periodic, so the average voltage across inductor will be 0. So if you take VL average equals to 0, or you equate the volt time area, VL average means the volt time area. If you calculate the volt time area, what will be the volt time area? The volt time area will be equals to Vs minus V naught. It has this particular value during on period, plus it has a value minus of V naught during off period. If this now equated to 0, you will get V naught equals to alpha Vs. So this will be the average output voltage of a buck converter. V naught is equals to alpha Vs. You know that alpha has maximum value. Alpha, the duty ratio has can be varied from 0 to 1. Okay, so you can see here always you will always get a voltage V naught which is equals to less than Vs. Okay, or step down converter. So buck converter is basically equivalent to step down chopper. Step down buck converter is also called step down chopper, and it is equivalent to what? Equivalent to a step down chopper in case of AC network. Okay, now always do this particular thing, and after this particular thing, do remember to do next thing, that is always equate output power to input power, that is P naught is equals to P input. So when you equate P naught to P input, what you will get? P naught is V naught into I naught, and P input is Vs into Is. So from here what will be the value of Is? What will be the value of Is? Is will be equals to V naught I naught upon Vs. V naught is equals to alpha Vs upon Vs into I naught. So from here you will get Is which is equals to alpha times I naught. Okay. Third thing is IL average. So here in this particular circuit, IL average is equals to I naught. Okay, and this is equals to V naught upon R. Now tell me what will be the value of the switch current? What will be the average value of switch current? So average switch current, you have written it alpha times IL average. Okay, you can see the figure. This switch current is the portion of the IL current present during the on period. Similarly, freewheeling diode current is the portion of IL current that present during the off period. So it is equals to alpha times IL average. It is equals to 1 minus alpha times IL average. Okay. So alpha times what is IL average? IL average is basically equals to alpha I naught. So IS switch current average value will be equals to what? Alpha times I naught. Similarly, freewheeling diode average current, this will be equals to what? 1 minus alpha times IL average or 1 minus alpha times I naught. So this is how you will calculate all the currents and voltage in the circuit. Okay. Now, what will be the value of ripple current? What will be the value of ripple current? Del IL. So the del IL is equals to alpha 1 minus alpha Vs upon FL in this particular case, and for a certain value alpha equals to, this is also a very important formula, del IL is equals to alpha 1 minus alpha Vs upon FL. For alpha equals to 5, you will get the maximum value of del IL. So the maximum value of del IL will be equals to Vs upon 4 FL if you put alpha to be equals to 0.5 here. Okay. So this is also an important formula. Now you can calculate I max. So I max will be equals to what? It will be equals to IL average plus del IL by 2, and you will calculate I min, which is equals to IL average minus del IL by 2. Okay. How do you calculate these particular things? See, I max, this particular value, if you want to calculate this particular value I max, this will be equals to this average value plus this amount. If you add this amount is del IL by 2. So when you add average value plus this IL, this amount del IL by 2, you will get I max. When you subtract, you will get I minimum. Okay. So this is how you will calculate I max and I min. You know the value of del IL average and you know the value of del IL. So just put and calculate I max and I min. After that, what will be the critical inductance? So if you calculate critical inductance, what will be the value of critical inductance? So how critical inductance is being calculated? Critical inductance LC. So at critical inductance, what will happen? Either you can put I minimum to be equals to 0. Critical inductance is that value of inductance for which the inductor current just become discontinuous. Okay, just become discontinuous means I minimum becomes equals to 0, or in other way you can say this IL average is become equals to del IL by 2, isn't it? Just see the waveform. If you are talking about discontinuous mode, this I minimum become equals to 0, or this IL average is exactly equals to del IL by 2. Okay, so this is the condition that you have to put. So when you put the values of IL average that we have calculated and del IL that we have calculated, you will get critical inductance, which is equals to 1 minus alpha R upon 2F. 1 minus alpha R upon 2F, this is what you will get as critical inductance. Now if I talk about the capacitor current, so what will be the value of capacitor current? Just tell me what will be the value of capacitor current. So isn't the capacitor current will be like this? So how do we get the capacitor current? See, inductor current is basically equals to capacitor current plus I naught, isn't it? Or the capacitor current will be equals to inductor current minus I naught, isn't it? Now average value of capacitor current is 0. You know that del IC average is equals to 0. So tell me from this waveform, if current IC is equals to IL minus I naught, means if you subtract I naught from this IL waveform, this waveform will be shifted and you will get a waveform like this, isn't it? You will get a waveform like this. So this time period is basically T by 2 and the stored charge during this period is del Q, and this amount of waveform is del IL by 2. Okay. So if I talk about what is the stored charge will be area of this particular triangle. So this is equals to half T by 2 into del IL by 2, or we may say del IL upon 8 F, okay, and del Q is also equals to C into del V naught. So what will be the ripple voltage? So the ripple voltage will be equals to del IL upon 8 FC, or if you put the value of del IL, which is equals to 1 minus alpha Vs upon FL, then you will get 8 F square C. So this is what, this is the output voltage or ripple in output voltage. So this is how you will calculate the ripple in the output voltage. Now critical capacitance, if you calculate critical capacitance, another important formula. So critical capacitance, this will be Cc. So at critical capacitance, what do we have? At critical capacitance we have V naught equals to del V naught by 2, okay. So V naught equals to del V naught by 2, or V naught is equals to alpha times Vs, and del V naught just we have calculated, this is equals to alpha 1 minus alpha Vs upon 16 F square C. So this will be subtracted, this will be cancelled out, and what will be the value of Cc? So Cc value will be equals to 1 minus alpha upon 16 F square L, okay, there is L also. So this will be the value of critical capacitance in case of a buck converter, 1 minus alpha upon 16 F square L. So these are all the important formulas in case of buck converter you have to remember, okay. What are the formulas? Average value of output voltage is what? Alpha times I naught. Average source current will be similar to what we have calculated, Is is equals to alpha I naught. Average inductor current is V naught by R. Switch will carry the portion of inductor current during alpha during on period, so it will be equals to alpha IL average. Freewheeling diode will carry the average of inductor current during off period, so it will be equals to 1 minus alpha I naught. Now put the value of I naught and get the values of them. Peak to peak ripple current is alpha 1 minus alpha Vs upon FL. This is maximum when alpha is 0.5, so it is equals to Vs upon 4 FL. I max you can calculate IL by IL average when added with del IL by 2. I min will be equals to IL average when subtracted del IL by 2. Similarly, critical inductance is calculated by this particular trick, and you will get the critical inductance here. Suppose if you forget some formula, it is quite easy to derive in case of buck converter if you just remember the circuit, okay. Now how do you calculate critical capacitance? This is how you will calculate the critical capacitance. So this is all about the buck converter. Now next circuit is boost converter. Second circuit that we have is boost converter. So in case of boost converter, we are having output voltage greater than the input voltage. What is the circuit diagram of boost converter? So the position of inductor is changed. This is the switch that we have, or also known as the chopper. So this is the chopper, this is inductor, and this is the value of voltage across inductor, this is the direction of current, this is also the source current, this is the Vs that we have. Then we have a freewheeling diode, and then capacitor, then we have resistor. So this is the circuit diagram of a boost converter that we have, okay. This current is IC. So this circuit is known as the boost converter circuit. Now see, what are the patterns of different waveforms? What are the patterns of different waveform? Just imagine, if suppose this is VL, let us draw the waveform first. It is VL that we have. After VL, let me draw IL. So this is IL, and after that let me draw the switch current. and after that let me draw the diode current. Okay, let's suppose this is the on period and let's suppose this is the off period that we have. So what will happen during on period and off period? See, during the on period when the chopper will be off, this portion of circuit will be active during on period. When the chopper is off, then we have this particular circuit to be active during the off period. So when the chopper is on, the inductor voltage will be what? It will be equals to Vs, isn't it? Vs is equals to Vl. When the chopper is off, then latter part of the circuit will come into play, and then this voltage VL will be equals to Vs minus V naught, isn't it? This voltage will be equals to Vs minus V naught. So this is Vs minus V naught. So this is your on period and this is your off period. Now what happens to inductor current? During on period inductor current rises and during off period inductor current linearly decreases. This is I min and this is I max. Now the average of inductor current in this particular case, that is IL average, this is equals to the source average current, isn't it? See, source will carry current permanent here, okay? See, when the chopper is on, the source current is equals to IL. When the chopper is off, this source current is transferred to the load current. So source is connected, source is connected to inductor and the chopper during on, and it will be connected to the load part during the off period. So this is what we will get. So IL average basically will be equals to what? IL average in this particular case, this will be equals to the average value of source current, okay? Because source IL is what? IL is basically the source current here, okay? Now if we talk about the switch current, so switch will carry current during the on period, isn't it? The switch will carry the current in the on period only. If I talk about diode, diode will current the same portion of the inductor current during the off period, isn't it? So if I calculate the average value of switch current, so I switch average, this will be equals to alpha times whatever we have, I am having as IL average. And if I talk about the I freewheeling diode, I diode average current, so I diode average current will be 1 minus alpha times whatever my IL average, isn't it? Because switch will carry the portion of inductor current during the on period, so its average value will be equals to alpha times IL average. Diode will carry the portion of inductor current during the off period, so its value will be equals to 1 minus alpha times IL average, isn't it? So these are the values of different currents in the circuit that we have. Now let us calculate one by one all the parameters. So if I calculate the first one, that is I apply volt ampere balance or VL average equals to 0. So what will happen? Vs into T on plus Vs minus V naught into T off, this will be equals to 0, okay? And when you will equate it, you will get V naught equals to Vs upon 1 minus alpha, okay? So from here you will always get V naught greater than Vs, that is boost operation. So a boost converter is equivalent to a step up converter as we have in case of AC circuit, okay? Now after that what other thing that we do? P naught is equals to P in. So P naught is basically V naught I naught and P in is Vs Is. So what will be the Is value? It is equals to V naught upon Vs into I naught. V naught upon Vs is basically 1 upon 1 minus alpha. So we have Is which is equals to I naught upon 1 minus alpha here, okay? Now after that I told you that IL average in this particular case is the Is average. So what will be the value of IL average? This will be equals to I naught upon 1 minus alpha, isn't it? Now what will be the switch current average value? So the switch current average value, this will be equals to alpha times the IL average value, okay? And IL average value you know is this particular thing, so you can put here and calculate this. After that what will be the diode's average current? So the diode average current is equals to 1 minus alpha times IL average. IL average you know is what? I naught upon 1 minus alpha, and this is equals to what? I naught. So ID average is basically what? It is equals to I naught, and this has to be this, and this has to be this. If this is coming something else, that would be wrong. Because why? See, during the off period, this is your IL current, and this current is going into capacitor, and so what will be IL average during off period? So during off period, you can see this is equals to IC average plus I naught average. IC average, you know, it is equals to 0. So IL average has to be during off period equals to I naught. And what is that current? That is the freewheeling diode current. So let me write here during off period, let me write here I freewheeling diode average current. So this is basically equals to what? I freewheeling diode during average is equals to I naught during off period, isn't it? And this is what we have calculated. That means we are going in the right direction. Everything that we have calculated is correct. Okay. Yes. So this is how we have calculated all the currents. Now after the current, what will be the maximum ripple current? What will be the peak to peak ripple current del IL? This is equals to alpha Vs upon FL in this case. What will be the value of critical inductance LC? So for critical inductance, what we will do? We will put IL average to be equals to del IL by 2, and from here when you calculate critical inductance, this will be equals to alpha 1 minus alpha R upon 2F. So this is the value of critical inductance that we have. After critical inductance, you will calculate the value of critical capacitance. Okay. So what will be my capacitor current in this case? So my capacitor current will be something like this. Now how do I get this particular thing? See, the freewheeling diode current is what? It is equals to IC plus I naught. So what will be my IC? If I subtract I naught from diode current, I will get IC. So you can see, if you subtract I naught from this ID current, so if you subtract this I naught current from ID current, you will get what? You will get a waveform like this, and that will be your IC current, isn't it? Now what will be the del Q? Del Q will be I naught into T on, and this is also equals to what? C del V naught. So what will be the value of del V naught? Del V naught will be equals to I naught into T on upon C, or you may also write it alpha I naught upon F C. For critical capacitance, V naught must be equals to del V naught by 2. So V naught is basically equals to I naught into R. Del V naught we have calculated alpha I naught upon 2 FC. So what you will get here? From here CC, that is critical capacitance, this will be equals to alpha upon 2FR, and this is a very important formula. So you can see, you can derive these formulas anytime. Okay, you can derive these formulas anytime. It is better, it is a better and recommended practice if you can remember this formula. But if you are not able to remember these formulas, you can derive these formulas of choppers anytime. Okay. So this is all about the buck boost converter. Third circuit that we have is buck boost converter. The third circuit that we have is buck boost converter. And what is the circuit of buck boost converter? The buck boost converter circuit is something like this. So in boost converter, we just replace chopper with inductor, and then we will get the buck boost converter circuit. This is IC, this is I naught, this is V naught. This is diode, this is inductor, this is inductor voltage, and this is inductor current. This is your chopper, and this is Vs, this is Is. Now what will happen? Let me draw the waveform. So first I will draw inductor current wave, inductor voltage waveform, that is VL. After that I will draw inductor current waveform, and after that I will draw the switch current waveform, and after that I will draw the diode current waveform. So I have to draw these following waveforms, and let me check what will be the different values that I will be getting during the on period and during the off period. So if this is VL, this is IL, and this is switch current, and this is the freewheeling diode current, or let me call it only diode. So what will happen during on and off period? See, when the switch will be on, Vs will be equals to VL. So during T on, what I will have Vs equals to VL or L DIL by dt. Okay. So my VL will be equals to Vs during the on time and during off time. So during off time, what I will have? See, during the off time, this VL is equals to minus of V naught, isn't it? This VL is equals to minus of V naught, isn't it? During the off time, you will be having minus of VL plus V naught equals to 0, or VL is equals to minus of V naught, or VL will be equals to V naught. So you will be having plus V naught here, okay? So I will be having VL equals to V naught here. So this is Vs and this is V naught. This is on period and this is my off period. What happens to inductor current? Inductor current will increase during on period and it will decrease during off period. And the average of inductor current will be IL average only here. It is not equals to I naught, or it is not equals to the source average current. It is IL average. Okay, it is known by its own identity here. This is I max, this is I min. What will be the switch current? The switch will carry the current similar to what we have during the on period. And what will the diode current? Diode will carry current what we have during the off period, the portion of inductor current that we have during the off period. So this will be my diode current. Now the average of switch current will be equals to alpha times, the average of switch current will be equals to what? It is equals to what? Alpha times which current? Tell me, alpha times which current? Alpha times IL average, that we are doing everywhere. This is equals to alpha times IL average, and the average of my diode current, this will be equals to what? This is 1 minus alpha times IL average. So this is how I will calculate source current, switch current average value and diode current average value. Okay. So these are the waveform that we will obtain in case of buck boost converter. Now tell me, if we calculate different parameters, that is VL average equals to 0. First of all, we have to equate the volt amperes. We have to calculate the volt time area from the inductor voltage waveform. So if you equate VL average to be equals to 0, that is nothing but equating the volt time area. So the volt time area is what? This is equals to this much. If now this is equated to 0, what you will get? You will get V naught equals to minus of Vs T on upon T off, or you will get V naught equals to minus Vs alpha upon 1 minus alpha. So you are getting a negative sign here. Okay. So if we talk about the magnitude, this is equals to Vs alpha upon 1 minus alpha. This negative sign is coming just because we have taken this particular polarity of output voltage. If you take negative, positive in the lower side and negative in the upper side, you will not get any negative sign. Okay. So I have taken this intentionally to let you know that there is a negative sign in the output voltage. Now for alpha less than 0.5, you will get buck operation, and for alpha greater than 0.5 you will get a boost operation. Okay. For alpha less than 5 you will get a buck operation, that is V naught will be less than Vs. Okay. V naught will be less than Vs, and for alpha greater than 5 you will get V naught greater than Vs, that is boost operation. Second thing that we do is just equate P naught to P input. So when you equate P naught to P input, what you will get? You will get what is the value of Is? Is will be V naught upon Vs into I naught. So V naught upon Vs will be equals to what? Alpha upon 1 minus alpha times I naught. So you have calculated Is, which is equals to alpha upon 1 minus alpha times I naught, isn't it? So we have calculated output voltage, we have calculated average value of source current. Okay. Now tell me, source current flows during the on period only, and after that the source is disconnected from the load. So the average value of source current will be alpha times the average value of IL, isn't it? Just tell me. So we will be having average source current equals to alpha times IL average current here. So from here what will be the IL average current? This is equals to Is average upon alpha, and you have just calculated Is average, which is equals to alpha upon 1 minus alpha times I naught upon alpha. This is equals to I naught upon 1 minus alpha. So what is my IL average? My IL average is I naught upon 1 minus alpha. So this is how you will calculate IL average. Once we have calculated IL average, then after that what will be the average switch current? So average switch current is alpha times the IL average, and this will be equals to alpha upon 1 minus alpha times I naught. And what will be my what will be my diode average current? This is equals to 1 minus alpha times IL average. So when you put the value of IL average, you will get I naught, which is quite evident. It has to be I naught. This case is quite similar to the boost converter case. So boost converter and buck boost converter had quite similarity in their operation. Okay. Now critical inductance, if I talk about critical inductance, and before that what will be the peak to peak ripple current? This is again equals to alpha Vs upon FL. Okay. After that what will be my critical inductance? So in order to calculate critical inductance, what I will do, I will just equate IL average to equals to del IL by 2, and from there I will get LC, which is equals to 1 minus alpha square R upon 2F. Okay, 1 minus alpha square R upon 2F. And critical capacitance is also calculated by the same formula that we have in case of boost converter, and which is equals to what? Alpha upon 2F, alpha upon 2F R. So these are the formulas of boost converter. So you can see how easily we have derived all formula, we have discussed all formulas. Okay. It is recommended that you know the operation of buck converter, boost converter and buck boost converter, because there was problem which were not related to direct formula. You must know the tricks of calculating this formula, and that I have discussed with you. How these particular waveforms have been drawn and how these particular values are being calculated, I have discussed with everything with you, and what are the conditions that are deriving these conditions. We have formulas, we have discussed. Okay. Why am I recommending you for this? Because I have seen there are questions in GATE exam. There are questions in GATE exam in which they are directly asking about, not about the formula, they are asking about the conditions. So you should know the conditions very well. Okay, and then you are then you will be done. Nothing will come in GATE exam from this particular topic which you will not be able to done, which you will not be able to do. Okay. So I hope this is understood to you. So just give me a reply. Is there any problem? Just give me a reply. Just give me a reply, student. Is there any problem? Are you getting what am I telling you? Just give me a reply. No, the discontinuous mode operation has to be discussed. So let me discuss one case of discontinuous mode and how the calculations are done. So let me talk about the buck converter case, and we will do all the analysis similar to in whatever converter we have. So if I talk about buck converter, so in case that we are having a discontinuous conduction operation, LC of buck converter and buck boost converter are same. Not at all. Not at all. Just see the formula. In case of buck converter, you have 1 minus alpha f upon 2r, r upon 2f. In case of buck boost converter, you have 1 minus alpha square r upon 2f. Okay. So let me discuss the discontinuous mode operation. So if I talk about the average inductor voltage, so average inductor voltage during on period, it will be equals to Vs minus V naught. It will be equals to Vs minus V naught, and during off period it is equals to what? It is equals to minus of V naught, but it is a discontinuous mode of operation. So this is the total time that we have, and this is the on time that we have, but off time is little reduced. Okay, this on time is what? This is equals to alpha t. This on time is basically alpha t, and let me call this time to be alpha 1 t. Let me call this time to be alpha 1 t. Okay, yes. So this is what I will get as VL average in discontinuous mode. Okay. Now if I talk about the current, so current will be like this. Since it is a discontinuous mode of operation, so you will be having only I max, and I min will be equals to what? It will be equals to 0. So this is what? This is alpha t, and this duration is alpha 1 t. Okay. So if I just apply this particular condition, VL average equals to 0, then what I will get? What I will get? Just equate the volt time area and you will get Vs minus V naught into alpha t minus V naught into alpha 1 t. Okay, so if you solve this particular thing, what you will get? You will get V naught equals to alpha upon alpha plus alpha 1 times Vs. Okay. So discontinuous mode, if discontinuous mode operation is being asked, you don't have to worry at all. Okay, you don't have to worry at all. Discontinuous mode they are talking about. So in discontinuous mode you have discontinuity. So VL average equals to 0. You have to apply the same trick here also to calculate the output voltage. Okay, so don't have to remember anything. If discontinuous mode operation came, there is no problem at all. See how easily we have done this particular thing. Now alpha must be, what is the condition for discontinuous condition? Alpha must be less than 1 minus alpha for discontinuous mode. Alpha must be less than 1 minus alpha for discontinuous mode of operation. Okay. Now what will be the del IL? So my del IL here is now only equals to I max, isn't it? This is only equals to I max, and this is what? This is IL current. So if I calculate IL current, average value of IL current, then the average value of IL current will be what? The area covered by this waveform. So 1 upon T, and the area of the portion half I max into alpha t plus half I max into alpha 1 t. Okay, and this is also equals to V naught by R. So just calculate this and just equate it. So what you will get? You will get what you will get from here? You will get half of I max alpha plus alpha 1. This is equals to V naught by R. Okay. So this is something, this is all necessary for discontinuous mode of operation. So this is nothing to discuss. That's why I am just discussing it about buck converter and leaving everything else over to you. This is how to do the buck discontinuous. This is how to deal the discontinuous mode of operation. Is that clear? Just give me a reply, bachcha log. Is that clear? Are you getting? Are you enjoying this lecture? Are you enjoying this revision? Just give me a reply. Everything is clear. Just give me a reply. Are you enjoying this revision class? So we are just done with semiconductor devices. We are done with phase control rectifier, and we are done with choppers as well. Now it's turn for the inverters. Okay, now it's turn for the inverters. So what inverter does, they convert fixed DC value into variable AC voltage. Okay, now before actually getting into the inverter, let me tell you the Fourier series of some basic functions, because you will be getting these waveforms again and again. So it is better to discuss how the Fourier series is being obtained for these waveforms. Okay. If suppose you have this square wave waveform, then what will be the Fourier series of this waveform? See, the Fourier series of this waveform will be what? This is equals to summation. This is equals to summation n equals to 135 to infinite 4 Vs upon n pi sin n omega naught t. So this is the Fourier series for this particular waveform. Now if suppose this waveform just changes its shape and it becomes something like this. If suppose now we have a similar waveform, but this particular waveform is now shifted by an angle alpha. So if this particular waveform is just shifted by this angle alpha, then what will be the Fourier series of it? The Fourier series of it will be n equals to 135 to infinite 4 Vs upon n pi sin n omega t minus n alpha. Okay. So if you have this particular waveform, the Fourier series will be this. If you have a shifted waveform, the Fourier series will be this much. If suppose this waveform is shifted towards the left, then you will be having an plus alpha here. Is that clear? So these will be very helpful for you. Now after these two waveform, we have third waveform with us, which is known as the quasi square wave waveform. So we have quasi square wave waveform like this. If suppose you have a waveform like this, okay, this is theta, this is pi minus theta, this is pi, and this is 2 pi. So if you have this particular waveform, then what will be the Fourier series of this particular waveform? So the Fourier series of this particular waveform will be, you will be having V naught t equals to summation n equals to 135 to infinite 4 Vs upon n pi cos n theta sin n omega naught t. So this particular term cos n theta will come if the waveform is quasi square wave waveform. Okay. Is that part of screen is visible to you? Just give me a reply. Is that portion of screen is visible? Swakar, just give me a reply. That wave portion of screen is visible. Just give me a reply. That portion of screen is visible. Okay. So quasi square wave, we have a waveform like this, and the result will be something that I have written here. After that, if suppose we have a stepped waveform like this, if suppose we have a stepped waveform like this. Okay, suppose this duration is pi by 3, this duration is 2 pi by 3 and this duration is pi. Similarly, if suppose this magnitude is Vs and suppose this magnitude is 2 Vs, okay, Vs and 2 Vs. If suppose we have these magnitude, then how to just find the Fourier series of this particular form? So see, we can divide this particular waveform into two portion. One portion you can just see the red portion. This is the red portion that is having a complete square wave, okay, and after that see we have a green portion in which we have only this portion of square wave which is quite similar to the quasi square wave, isn't it? See the red and green portion. The red portion of waveform is what? Red portion is a complete square wave and the green portion is what? It is a kind of a quasi square wave, okay. So what will be the complete square Fourier series of this particular thing? So Fourier series will be, first of all you will write for a square wave. So for a square wave you will be having 135 to infinite 4 Vs upon n pi sin n omega naught t, plus for quasi square wave portion you will be having, you will write by this particular, referring to this particular thing, and it will be equals to 4 Vs upon n pi cos n theta. So what is theta here? Theta here is pi by 3. So you will write sin n pi by 3 sin n omega naught t. So the resultant will be the resultant of both of them, okay. So what will be the resultant of both of them? Let's just solve them. So V naught t, this is equals to summation n equals to 135 to infinite 4 Vs upon n pi, we will get 1 plus cos n pi by 3, isn't it? Yes. Why I have written sin here? It will be cos here, okay. So it will be equals to cos 1 plus cos n pi by 3 sin n omega naught 3 t, okay. Now this cos n pi by 3, this will be equals to minus 1 for n being multiple of 3, for n being multiple of 3. So what will happen? You will get V naught t equals to 0 always. So what will happen? All the multiples of 3 will be out from this waveform, okay. And this 1 plus cos n pi by 3, yeah, just leave it, just leave it. So what you will get? You will get V naught t, this is equals to what happens? N equals to now 1 5, or we may just write it n equals to 6k plus minus 1 means 5, 7, 11, 13 and so on. So this will be the expression that you will get for this particular waveform. So tell me, is this helpful? Is this helpful for you? If you have a sine, if you have a square wave, its Fourier series is 4 Vs upon sin n omega t, and all even, all odd harmonics will be present. If you have a shifted waveform, just shift the angle, okay. Let's everything remains the same. If you have a quasi square wave, what will happen? A cos n theta term will come. What is theta? Theta is that particular angle, okay. So a cos n theta term will come. If you have a stepped waveform, okay, see here Vs is what? Vs is the magnitude. So whatever is the magnitude written here, you have to just write the magnitude here. For our case it is Vs, so I have just written Vs here. So this particular waveform is the summation of two waveform, one complete square wave and a quasi wave, okay. So when you solve this, what happens? You will see that all triple n harmonics will be eliminated. All triple n harmonics will be eliminated, even harmonics will be eliminated, and you will be having a waveform like expression like this. Is that clear? Just give me a reply. This particular analysis will be very helpful for you, okay, while analyzing the inverters. So let me discuss single phase half bridge VSI first. So what will happen in a single phase half bridge VSI? What is the circuit diagram of it? So we have Vs by 2 and Vs by 2, two voltages, and after that we have thyristors and anti-parallel diode. This is the load. This is T1, this is T2, this is D1, this is D2. Okay. So let me discuss the voltage waveform for different loads here. So first of all, let me draw the voltage waveform, then I will draw the let me just utilize the space very effectively. Suppose this is my voltage waveform. So I will be getting a voltage of Vs by 2 and minus Vs by 2. This is when T1 is on and this is when T2 is on. So when Ts is on, this is my output voltage. So what will happen? We will trigger both these thyristor one by one. So when my T1 will be on, my output voltage will be Vs by 2. Okay, and when T2 will be on, my output voltage will be minus Vs by 2. Okay. Now if I talk about the current, so what will be my current? So my current for resistive load, will be similar to what I have in case of this particular the shape of it will be quite similar to that I have in case of voltage. So in case of resistance, the output current will be having the same shape as that of voltage. In case of pure inductor, or in case of, let me discuss in case of RL load, in case of RL load, the wave, it will be exponentially increasing and decreasing. So in case of RL load, it will be exponentially increasing and exponentially decreasing. So this is I naught, this is for R load, and this is for RL load. Okay. It will be exponentially increasing and decreasing. This is I max and this is I min here. So this is I max and I min I am having here. Now if I talk about a pure inductive load, so in case of a pure inductive load, my waveform will be like this. Linear waveform I will be having. I naught for L load. Okay. So in case of RL load, you can see this is the duration when so let me mark these durations. So you can see this is the duration when this is when T1 will be conducting and this is when D2 will be conducting. After that, this is when T2 will be conducting and this is the duration where D1 will be conducting. Okay. Similarly, here we will be having a D1 conducting and here we will be having T1 conducting. Here we will be having D2 conducting and also here we will be having T2 conducting. Okay. So in case of RL load and L load, you can see we are getting a different waveform from the output voltage. So whenever a thyristor is conducting, you can see whenever a thyristor is conducting, both V0 and I0 are positive, whether it is RL load or whether it is L load, both are positive. So what will happen? Whenever there is a thyristor conducting, when T conducts, output voltage and output current both are positive. So power transfer takes place from source to load. Okay. But you can see whenever a diode is conducting, whenever a diode is conducting, see, when D2 is conducting, the voltage is negative but the current is positive. Okay, so when D2 is conducting, what happens? V0 is negative but current I0 is positive. So what will happen? Power will be negative, so power will flow from load to source. Similarly, when D1 is conducting, what will happen? When T1, T2 are conducting, when T1 and T2 are conducting, we are having, sorry, I cannot generalize this particular thing. This is for T1, okay. So when T1 is conducting, V0, I0 are positive, power flows from source to load. When D2 is conducting, what will happen? V0 is negative but I0 is positive, so power will be negative, so power is flowing from load to source, okay. Similarly, I can write when T2 is conducting, so when T2 is conducting, V0 is negative and I0 is negative as well, so power will be positive, so my power flows from source to load, okay. And similarly, when D1 will be conducting, so during D1 what will happen? I0 is negative, V0 is positive, so power is negative and power flows from load towards source, okay. So this is what you have to remember. Whenever a diode conducts, power flows from load to source, and whenever I have SCR conducting or thyristor conducting, power flows from, or we can say that power is positive, output power is positive, power flows from source to load, or we can say the power is negative, okay. So always remember this fact, whenever we have thyristor conducting, the power is positive and power is being flowing from source to load. DC is being converted into AC. Whenever we have diode conducting, the power is being flowing from load to source, okay, that is AC is being converted back into DC. Is that clear? Now after that if I talk about single phase full converter, single phase full converter, full bridge VSI, then in that case what will happen? What will be the circuit diagram? Its circuit diagram will be something like this. We have Vs here, it is just double the half bridge inverter, so see, this is V0 I0, let me just reverse the polarity. So this is T1, this is T2, this is D1, this is D2, this is T3 and this is T4, this is D4 and this is D3. So this is my full bridge VSI. So in single phase VSI, in half bridge VSI, we are having one thyristor conducting at a time. Here we will be having two thyristors conducting at a time. T1, T2 and T3, T4. Similarly, T1 transfer its positive current to D2 in case of half bridge inverter. Here T1 will transfer its current to what? Let me just draw the waveform for one case. So here two thyristors will be conducting at a time. So this is T1, T2 conducting for this particular time, and this is T3, T4 conducting for this particular time. And if I talk about RL load, in case of RL load, what will happen here? T1, T2 will be conducting this particular current, and this particular current is being conducted by D3, D4. Again I will be having T3, T4 conducting here, and again I will be having D1 and D2 conducting here. Okay, so this is how the different switches will operate. This is V0, this is I0 for RL load. Now if I talk about RLC load, then my waveform will be something like this. So my waveform will be this waveform. This angle is what? This angle is known as the phi angle, and this waveform I am having for RLC load, where XL is greater than XC. XL is greater than XC or over damped case. Okay. Similarly, if I choose an under damped case, this current will be leading. Okay, this current will be leading by an angle phi. So here T1 and T2 conducts, here D3, D4 conducts, here again T3, T4 conducts, and here again D1, D2 are conducting. See, this is for over damped case. If I choose under damped case, this will be my waveform, and what will happen here? So what will happen here? T1 and T2 will be conducting, and then I will be having D1, D2 conducting here. Then I will be having T3, T4 conducting here. Okay. Similarly, D3, D4 will be conducting here. Okay. So I will be having this particular waveform for over damped case where XC is greater than XL. This is under damped case. Okay. So this is the waveform for single phase full bridge VSI for all the cases that we have. Now how to calculate this particular angle phi? This particular angle phi, how do you calculate? In case of we have over damped case, so if suppose we are having over damped case means XL is greater than XC, then this particular omega TC will be equals to phi, or this TC will be, or omega TC will be equals to phi, or TC will be equals to phi upon omega or 1 upon omega, and this phi will be equals to tan inverse XL minus XC upon R. In case I am having over damped case, under damped case, sorry, in case I am having under damped case, so in under damped case I am having XC greater than XL, then my TC will become, then this TC will become 1 upon omega tan inverse, I am having XC minus XL upon R. So in that case what will happen? I0 leads V0 by angle phi, and here I am having I naught lakhs V naught by phi. Okay. So, this is how we will see the variation of current in case of half bridge and full bridge inverter for different cases. For R case, for L case, for R case voltage waveform and current waveform will be having the same shape. For RL shape, for RL load, the current waveform will be having exponentially increase and exponentially decreasing nature. Okay. Now, what is the maximum and minimum value of current I max and I min in case of RL load? What is the value of this? This is equals to Vs upon R 1 minus e to the power minus t by 2 tau upon 1 plus e to the power minus t by 2 tau. Okay, where tau is what? Tau is L by R. So, by using this particular formula, you can calculate the maximum and minimum current. Okay. In case of RLC load, the load is the current is free from the harmonics and its shape will be perfect sinusoidal. If the load is overdamped case, then what will happen? The current will be lagging the voltage. If the load is underdamped case, then the current will be leading the voltage by an angle phi. And how do you calculate that angle phi? By using this particular formula, you will calculate the angle phi. Okay, or the circuit turn off time. Okay, this is how you will calculate the circuit turn off time in different cases. Is that clear? Just give me a reply. Now, what will be the Fourier series? In case of half bridge converter, in case of half bridge converter, in case of single phase half bridge converter, what will be my output voltage? So, in case of half bridge converter, my output voltage Fourier series will be n equals to 1, 3, 5. See, it is a simple case of what? A simple square wave. So, we have 4 Vs, and in case of Vs, we are having Vs by 2 magnitude here. Okay, and in case of full bridge rectifier, full bridge inverter, we are having this magnitude equals to Vs. So, what will happen? This will be equals to 4 Vs by 2 upon n pi sin n omega naught t. So, ultimately this will become n equals to 135 to infinite. This will become 2 Vs upon n pi sin n omega naught t. Okay. And in case of half bridge inverter, in case of full bridge inverter, single phase full bridge inverter, in case of single phase full bridge inverter, I am having output voltage Fourier series which is equals to 4 Vs upon n pi sin n omega naught t exactly, isn't it? Isn't it? This will be equals to this much. Now, if I calculate, if suppose in case of single phase full bridge converter या full bridge inverter, if we take this particular case where we are having V naught equals to n equals to 135 to infinite 4 Vs upon n pi sin n omega naught t. Now, what will be the fundamental RMS component here? The fundamental RMS component here will be this much, or we may write it 2 root 2 upon pi into Vs. What is the total RMS value of output voltage? Since is it a square wave, it will be equals to Vs. Then tell me what will be the CDF or distortion factor. This is equals to fundamental component upon total component. So, when you will calculate, you will get 2 root 2 upon pi here. After that, what will be my THD? So, my THD will be 1 upon under root CDF square minus 1, or I will get 48.34% of THD here. Okay. Is that understood? So, this is how you will calculate. Several times I have seen the problems in the exam where they have asked what is the ratio of fifth harmonic component to the fundamental component. Means they are asking you to calculate V naught fifth RMS upon V naught fundamental RMS. So for that you have to just know what is the Fourier series representation, and then you will be able to calculate ratio of whatever component is being asked. Is that clear? Give me a reply if it is clear. After that, let me discuss single phase CSI, current source inverter. Okay, so what will happen in case of current source inverter? So we have a strip DC current source here, then we have thyristors, and this is the load. Okay, this is T1, this is T2, this is T3, and this is T4. This is the current source that we have. This is what? This is the current source that we have. Okay, this is Vs, this is Ls, and this current is Is current. Okay, so what is the features of CSI? There is no feedback diode. There is no feedback diode present in CSI, and load must contain capacitor. Okay, load must contain capacitor, and other advantage is one thyristor is getting off and the other is getting on. To the first thyristor is getting commutated by with the help of the load. Okay, so there is no need of feedback diode in this current source inverter. Load must contain a capacitor. These are the must conditions. Now what will happen? See how the voltage waveform and current waveform will vary. So if suppose this is the I naught waveform, then we have the V naught waveform, and then suppose we have the V input waveform, V input. So let's see what will happen with these things, how these things are varying. So what will happen when T1 and T2 are on, I naught will be equals to Is, and when T3 and T4 are on, I naught will be equals to minus of Is. This is equals to Is and this is equals to minus of Is when this is T1 and T2 on, and this is when T3 and T4 on. जब T1 T2 ऑन होंगे तो I नॉट इक्वल्स टू Is होगा, और जब T3 T4 ऑन होंगे तब Is इक्वल्स टू I नॉट इक्वल्स टू माइनस ऑफ Is होगा. वोल्टेज वेवफॉर्म का क्या होगा? वोल्टेज वेवफॉर्म विल बी लाइक दिस. How we are getting this particular waveform? See, across C what will happen? IC is equals to C dV naught by dt. So by using this particular formula, I am getting output voltage. Okay, I naught equals to C dV naught by dt. This particular formula, if I use, I will get this particular formula. So if I am having a rectangular pulse as I naught, I will be having a triangular pulse at output voltage by using this particular formula. What happens to V input? See, V input, what will happen to V input? What is voltage V input? V input is this particular voltage. V input is this particular voltage. So what will happen to V input? When T1 and T2 are on, V input is equals to V naught. V input is equals to V naught when T1, T2 are on, and V input is equals to minus of V naught when T3 and T4 are on. So what I will get? I will get a waveform like this as input voltage waveform. So you can see here the output voltage time period is T naught and input voltage time period is T input. So what is the relation that I am having? T output is basically 2 times T input, or we may say 1 upon F naught is 2 upon F input, or we may say F input is basically 2 times F naught here. So this is all about CSI, the current source inverter. Okay. Now there is one problem with CSI, the load must contain capacitor. Okay. So there is a problem that capacitor may discharge directly across the thyristors and they may get damaged because they will experience a very high reverse bias voltage, isn't it? So the solution provided for this is ASCII, auto sequential commutated inverter. Auto sequential commutated inverter. They remove just the problem of capacitor getting discharged directly across the devices. Okay, so this provide a solution, and what is the solution that it will provide? See, what it will do is that we will use diode. Okay, we will use diode like this to just avoid this particular problem of capacitor directly being discharged across the load. So this is T1, this is T3, this is T2 and this is T4. So we will be using these diodes which will just remove this particular problem. So this is C1 and this is C2 and this is my load R. Okay. So by using auto sequential commutated inverter, I just remove the problem of capacitor being directly discharging across the load. We will use a diode in between. Okay. Now the maximum switching frequency of auto sequential commutated inverter limited to F max is basically equals to 1 upon 4 RC, where C is what? C is the series combination of C1 and C2, which is equals to 2C. Let me write it. If C1 and C2 are equal to each other, or in other way, let me just use it. C1, let me just write C1 and C2 are in series. Okay, so what will be the C? What will be the equivalent C? C equivalent basically equals to C1 C2 upon C1 plus C2. So this is how you will calculate the maximum switching frequency of a auto sequential commutated inverter. Is that clear? After that, let me move towards the 3-phase VSI. The 3-phase VSI. So in 3-phase VSI, we are basically having first inverter, which is 180-degree mode inverter. 180-degree mode inverter. So what happens in 180-degree mode inverter? Each switch will conduct for 180 degree of a cycle. And let me draw the 3-phase VSI. So this is my 3-phase VSI. So this is the three-phase VSI. It is composed of three half-bridge inverter, isn't it? It is basically a combination of three half-bridge inverters. So we have T1, T3, T5, and we have T2, T4, T6 and T4. Okay, so we are having this combination. This is D1, D3 and D5. This is D2, this is D6 and this is D4. So this is my three-phase VSI. So in three-phase VSI I am having 6 switches. Each switch will conduct for 180 degree of a cycle, and we are having 6 switches. 1, 3, 5 are the positive group and 2, 4, 6 are the negative group. Okay, so what will be the so each switch will conduct for 180 degree of a cycle. So let me just come to the voltage waveform that I will be getting here. So if you remember the voltage waveform of phase voltages, it is equals to Vs by 3, 2 Vs by 3 and then Vs by 3. Then Vs by 3, 2 Vs by 3 and then again Vs by 3. So this is the voltage waveform that I will be getting. This is pi by 3, this is 2 pi by 3 and this is pi. This is Vs by 3 and this is what? This is 2 Vs by 3 that I am having here. And this is again Vs by 3. So this is the phase voltage waveform that I will be getting. And if I talk about the line voltage waveform of a phase VRY, I will be getting something like this. A quasi square waveform I will be getting. So this is 2 pi by 3 and this is pi and this magnitude is Vs. So these are the phase voltage and line voltage waveform that I will be getting in case of a 180 degree VSI. So if I just calculate the line voltage RMS value, or it is also equals to V line RMS, then it is equals to what? This is equals to Vs under root 120 upon 180, or I will be getting VL RMS. This is equals to under root 2 by 3 of Vs. So from here if I calculate the phase voltage RMS value, then phase voltage RMS value will be equals to what? It is equals to VL upon root 3. So I will be getting root 2 upon 3 Vs here. So these are the formula of calculation of line voltage and phase voltage. You do have to remember these formulas only and they will do the trick for you. So if you can remember these formula, everything will be done. Now, so we are having line voltage. We are having line voltage equals to what? We are having line voltage equals to under root 2 by 3 of Vs. We are having phase voltage and all are the RMS value, which is equals to under root 2 by 3 Vs. Then after that I am having I phase current, which is equals to what? V phase upon R. I can calculate it by this. After that if I calculate the power, this is equals to either 3 I phase square R, or I will calculate it from 3 V phase square upon R. This is very important. Okay. If suppose this is a star connected load, if this is a star connected load, I will be having line voltage and phase voltage to different values. But if suppose the load is delta connected, then you will use only the line values. Okay, then line voltage will be equals to the phase voltage. So if it is a delta connected load, use only line values, don't use the phase values. Okay, but if it is a star connected load, line values and phase values of voltage will be two different things. Okay. Now what will be the Fourier series of phase voltage? Now if I talk about the Fourier series of phase voltage, so see, phase voltage is having a stepped waveform. Okay, so phase voltage is having a stepped waveform. So what I have told you, in case of a stepped waveform, what you will get, what is the magnitude here? Magnitude here is Vs by 3. Okay, So what you will get? You will get 4 Vs by 3 upon n pi, 4 Vs upon 3 upon n pi. After that, what you will have? You will have 1 plus cos n pi by 3 sin n omega naught t. Okay, what is the value of sin 1 plus cos n pi by 3? So 1 plus cos n pi by 3, 1 plus cos n pi by 3, this is having a value of 3 by 2 for n equals to 6k plus minus 1. So ultimately my formula will become n equals to 6k plus minus 1 for what I will get here? 3 and 3 get cancelled. I will be getting 2 Vs upon n pi sin n omega naught t. So this is the Fourier series for my phase voltage, okay, and this is free from even and triplen harmonics. This is free from even and triplen harmonics. Is that clear? So this is the Fourier series of the phase voltage waveform. Similarly, if I calculate the Fourier series of line voltage waveform, my Fourier series for line voltage waveform will be what? Just see it. I am having this particular waveform here, okay. So if I just shift this particular waveform by an amount pi by 6. So if I just shift this by pi by 6, so this will be what? This will be 5 pi by 6. Okay, so this will be 5 pi by 6. So if this is a quasi waveform, and this particular quasi waveform when shifted by pi by 6 amount, I will be getting this particular waveform. So what is the Fourier series of a quasi waveform? The angle will be here pi by 6. So how do I write this particular waveform? N is equals to 6k plus minus 1. I will be having 4 Vs upon n pi, angle theta is cos n pi by 6, and I have shifted the waveform by an amount n pi by 6. So this is my voltage Fourier series for line voltage that I will be having. This is the Fourier series for phase voltage that I will be having. So if you can remember this formula, that will be so good. If you are not able to remember this formula, then use the tricks that I have told you initially in the starting of this inverter chapter, how to calculate the Fourier series of a square wave, a shifted square wave, a quasi square wave, and a stepped square wave. If you just remember these formula, and if you are able to correlate the waveform that you have to remember, this is something that you have to remember, then you can calculate the Fourier series very easily. Okay. Now here if you calculate the distortion factor, the distortion factor is basically equals to 3 by pi, and if you calculate THD, it is equals to 31%, and they are free from even and triplen harmonics. Just remember this fact. Okay. So this is all about the 180-degree inverter. Now if I talk about 120-degree inverter, 120-degree mode of inverter, 120-degree mode, 3-phase VSI. So in 120-degree mode inverter, what will happen? The circuit diagram will remain the same, and what will happen? Each switch will conduct for 180 degree of a cycle. So each switch will conduct for 180 degree of a cycle. Now if I draw the phase and line voltage waveform, so the phase voltage waveform will be something like this. We are having Vs by 2 amount, so I will be having a phase voltage waveform which is something like this, a quasi square wave I will be getting. So this is 2 pi by 3, and this is pi, and this magnitude is what? Vs by 2 and minus Vs by 2. This is my phase voltage waveform. And if I talk about the line voltage waveform, then my line voltage waveform will be something like this. This magnitude that I am having is Vs by 2 and Vs, okay. This value is Vs by 2, this value is again Vs. So this is my line voltage, okay. Now I leave it up to you. Just referring to the concepts of writing a Fourier series of square wave, quasi square wave, shifted square wave. Just you can write the waveform Fourier series expansion for this, okay. But before that, just calculate the RMS value of phase voltage. So VR RMS, that will be equals to what? So VR RMS will be equals to Vs by 2 under root 120 upon 180, or Vs by 2 under root 2 upon 3, or we may write Vs upon under root 6. So the phase voltage or VR RMS, this is equals to what? Vs upon under root 6. So this particular formula we have obtained for phase voltage. Now line voltage will be what? Now tell me what will be the value of line voltage. So VRY RMS, this will be equals to what? Root 3 times VR RMS, and then this will be equals to what? This will be equals to Vs upon under root 2. So this is the value of line voltage that you can obtain here, okay. So this is the way how we can obtain the phase voltage and line voltages here. After that, by using the same phenomena of writing the Fourier series waveform, what will be the Fourier series expression for the phase voltage? This will be equals to n equals to 6k plus minus 1. Just using the concept that we have discussed, it will be equals to 2 Vs upon n pi cos n pi by 6 sin n omega t plus n pi by 6. Similarly, if I write the Fourier series of line voltage, I will be having n equals to 6k plus minus 1 to infinite. I will be having 3 Vs upon n pi sin n omega naught t plus n pi by 3. So this will be the Fourier series expression for, and the value of distortion factor will again be 3 by pi, and THD, this will be again equals to what? This will be equals to again this will be equals to 31%, and the power factor here will be equals to 3 by pi cos alpha, okay. The power factor will be 3 by pi cos alpha, or power factor. Why do we need this power factor? We don't have to calculate this. This 3 by pi cos alpha, this formula we will use in case of three phase full wave phase control rectifier. The power factor formula will be 3 by pi cos alpha, okay. Just remember that formula as well. I think I have missed that formula there. So the power factor in case of three phase full wave converter, full wave phase control rectifier, will be equals to 3 by pi cos alpha, okay. So this is the Fourier series for line voltage and phase voltage in case of 180 degree mode converter that I will obtain, okay. Now coming to another important topic, that is the pulse width modulation, okay, or voltage control of inverter. So voltage control of inverters or pulse width modulation or PWM technique, okay. So first of all, let me discuss the very first technique, single pulse width modulation. Single pulse width modulation. So in single pulse width modulation, what do we have? In single pulse width modulation, I am having, this is my reference voltage VR, and I am having my control voltage which is equals to this much. So I will be getting a pulse of output voltage at the output like this. This pulse duration is what? This pulse duration is 2D, and this is my V naught. So V naught RMS will be equals to what? V naught RMS will be equals to, this is Vs, this is my carrier voltage. V naught RMS, this will be equals to V naught RMS, this is equals to Vs under root 2D upon pi. This is what I am having here. Okay, so V naught RMS will be equals to Vs under root 2D upon pi. You can see here, or let me just elaborate it more. So V naught RMS that I have obtained is Vs under root 2D upon pi. Now if I vary this pulse, you can see output voltage will also vary. If I vary this pulse, output voltage will also vary. Okay. Now what if I have to write the Fourier series for it. So see, this is pi by 2, and if suppose this angle is theta, then this length is d, then theta is what? Theta is basically pi by 2 minus d. Okay. So what is the Fourier series that we have? The Fourier series that we have is equals to n equals to 135 to infinite a quasi square wave. I have a Fourier series of 4 Vs upon n pi cos n theta sin n omega naught t. So if I just put theta equals to pi by 2 minus d here and then solve it, I will get sigma 135 to infinite 4 Vs upon n pi sin n pi by 2 sin nd sin n omega naught t. So this will be my Fourier series expression in case of single pulse width modulation. Okay. Now from here you can see this is the output voltage expression. Now from here you can see if this particular, let me write this again, V naught that I have obtained is equals to n equals to 135 to infinite 4 Vs upon n pi sin nd sin n pi by 2 sin n omega naught t. Now you can see V naught will be 0 if this nd is equals to pi or d equals to pi by n, or 2d equals to 2 pi by n, or 4 pi by n, or 6 pi by n until 2d is less or equals to pi. Okay. So this is the pulse length referring to this condition. Okay. So in order to eliminate third harmonic, suppose you wanted to eliminate the third harmonic, what will be the pulse length? Your pulse length will be 2 pi by 3, that is 120 degree. And if you want to eliminate fifth harmonic, your pulse length will be 2 pi by fifth plus 4 pi by fifth, that is 72 and 144 degree. Okay. So until and unless you will get 2d value less or equals to pi, you will just keep on calculating. Okay. So this is all about single pulse width modulation. After that we have multiple pulse width modulation. So the second technique that I have is multiple pulse width modulation. And what are the important formulas related to multiple pulse width modulation? We have following formula regarding this: number of pulses fed per half cycle, this is equals to N, and this is equals to f of C upon 2 FR, where FC is what? Carrier frequency, and FR is what? Reference frequency. Okay. Then pulse width of each pulse width, we may call it each pulse width. Then each pulse width is equals to 2D upon N, which is equals to pi upon N 1 minus peak of VR upon peak of VC. So these are the two important formulas that we have. And one more thing, that is gamma extension, we may calculate it by pi minus 2D upon N plus 1 minus D upon N. Okay. So by using these particular formula, you can do all calculation regarding MPWM. So I have not seen any of the questions coming so far now from this particular topic, but maybe this may come in your paper as well. After that, let me discuss the third important technique, which is sine pulse width modulation. Sine pulse width modulation, that is SPWM. Now in sine pulse width modulation, we have two cases. The first one is when peak of the carrier is coincident with 0 of reference In that case, when peak of carrier is coincident with the 0 of reference, number of pulses fed per half cycle will be FC upon 2 FR. Okay, number of pulses fed will be FC upon 2 FR. But in second case, when peak of carrier, I may write it, when 0 of carrier, 0 of both, okay, 0 of carrier and 0 of carrier and 0 of reference is coincident, then in that case number of pulses fed per half cycle will be equals to FC upon 2 FR minus 1. Okay. So these are the important formula regarding sine pulse width modulation. Apart from that, we have modulation index. We have modulation index, which is denoted by MA, and it is equals to peak of reference upon peak of carrier. It is the ratio of peak of reference to the peak of carrier. So this is what this is called as the modulation index. Second thing that we have, this is modulation index that we have with us. And after that, next formula is a frequency modulation index, M of F, this is equals to F of C upon F of R. Okay. Then next important formula is, and value of MA must be less than 1 for linear modulation, which is referred for linear modulation. And after that, one more formula that I am having is fundamental peak voltage, this is equals to modulation index time VDC. Fundamental peak is modulation index time VDC in case of full converter, because in case of full converter I am having VDC voltage or VS voltage. Let me write it VS because we have used VS here, MA into VS. And this fundamental peak voltage, this is equals to MA or Vs upon 2 in case of what? In case of half converter. In case of half converters. From the last 5 years, out of 5 times, 3 times there is a problem from this particular question. Okay, from this particular formula I have seen problems coming there. Okay, see, this is a peak value. If you are asked to calculate the RMS value, just divide this particular formula by amount root 2. Okay, this is what? This is peak value. That's why I have written peak here. Okay, so fundamental peak is equals to modulation index time Vs if it is full converter, Vs by 2 if it is half converter. So 5 out of 3 times I have seen this particular formula has been used for solving the gate problems. Okay, another formula that I am having that is more important, order of harmonics, order of dominant harmonics. This is equals to 2n plus minus 1, where n is number of pulses fed per half cycle. Okay, n is what? N is number of pulses fed per half cycle. So if you increase the number of pulses fed per half cycle, the order of harmonics will be increased. Okay, and you know, higher order harmonics are easy to be filtered out. So it is a better practice to increase the number of pulses fed per half cycle. Is that clear? Yes. So this is the end of the revision of this subject, power electronics. So I wish you all the best and all the success in the gate exam that is going to happen within a week. Okay, so all the best for the gate exam. I hope this revision would have helped you out in a manner you exactly wanted it. Okay, so we have just revised all the important formula, we have discussed all the important tricks needed to solve the questions of power electronics in paper. So just if you have already completed power electronics, thank you Swakar, I hope it will help. So if you have already completed power electronics, just go through them once again, and this will help out in revising power electronics effectively in a very less time. If you haven't completed power electronics yet and you are about to complete the power electronics, or you are just now haven't started the power electronics, in that case also just go through once about this lecture and you will get a feel of the power electronics. Nothing, mind my words, nothing will come beyond what we have discussed in this class today. So I wish you all the best for the coming gate exam. May you get a great score and a very good rank. So all the best, students. And from 5:30 we are having control system lecture of Ankur sir. So stay connected to revise control system from 5:30. Okay. And after that on 26 I will be revising the subject with you, the power system. So together we will revise the subject power system. So I will be waiting for you on 26 as well. So just note down the date and just save the date on your calendar. 26 from 1 PM onwards we will be revising power system as well. So I hope it will help you. All the best for the gate exam. All the best for the coming future as well. Thank you, students.